Tuh kan nih gurunya ribet banget nih, susah. Kayak gimana nih aku tengah. Ih, gurunya nggak jelas nih. Langsung sesi 2 aja mah ya. Aduh. Selamat pagi Bu Nelly.
Selamat pagi. Selamat pagi semua teman-teman. Belum partisipannya belum semua ya. Siapa yang belum? Di absen dong. Di ini maksudnya terus dipanggil gitu.
Ya, saya coba diingatkan di grup Bu.
Iya, selamat pagi sekali lagi. Assalamualaikum warahmatullahi wabarakatuh. Saya cuma ambil waktu 5 menit gitu ya pagi ini. Kita udah di hari keempat, mudah-mudahan teman-teman masih bersemangat gitu mengikuti training ini. Jadi mungkin saya terima kasih yang dari Papua, udah jam berapa di sana ya, udah siang. Jadi terima kasih buat Bapak Ibu yang menjadi peserta dan saya ngikutin dari hari pertama. Menurut saya teman-teman sudah sangat aktif lah ya untuk sharing. Sebenarnya ini mungkin lebih ke sharing pengetahuan. Dan kalau bagi saya pribadi sih apa yang mereka sampaikan itu membuat saya berpikir bagaimana orang lain itu bisa lebih lebih membahas Indonesia itu secara luar biasa. Berarti kan Indonesia itu berarti memang benar-benar laboratorium gitu ya bagi penelitian, bagi orang-orang akademis, sehingga mereka tertarik untuk melakukan analisa terhadap data-data di Indonesia. Dan kita berharap bahwa sebenarnya training ini nih semacam brainstorming juga bagi kita dan menjadi, kalau saya ikuti kemarin itu dari beberapa pertanyaan teman-teman itu justru next yang harus dilakukan gitu ya. Mereka juga belum melakukan. Nah, itu yang berarti kan itu menjadi harusnya kita anggap menjadi bagian dari tugas kita ke depan gitu. Jadi kalau bagi saya sangat membuka wawasan gitu. Saya bukan orang geofisika tetapi saya bisa paham secara lebih clear gitu kondisi kita dipandang dari sudut pandang ilmu geofisika gitu. Mudah-mudahan teman-teman merasakan hal yang sama. Kemudian yang kedua adalah saya pikir bagus kalau teman-teman terutama yang dari daerah ya. Seperti contoh kemarin yang Gunung Sitoli, ya coba dibahas Gunung Sitolinya lebih dalam gitu kan. Karena kan setiap daerah pasti berbeda ya. Kayak berbeda gitu kenapa-kenapanya, question and apa yang menjadi pertanyaan di situ mungkin berbeda, Papua akan berbeda gitu ya. Nah, kalau bisa seperti itu baik sekali kalau kita bisa berdiskusi. Dan jadinya ke depan kita juga tahu, oh harusnya yang harus kita lakukan setelah ini apa ya, gitu kira-kira gitu. Kalau bagi saya sih, saya berharap banyak gitu dari materi selama 5 hari ini, kita benar-benar mendapatkan pemikiran yang pengetahuan ataupun ide-ide baru gitu untuk kita ke depan. Jadi bukan berarti mereka lebih tahu, enggak. Jangan-jangan kita lebih tahu, tetapi mungkin kita belum melakukan seperti yang mereka lakukan gitu ya. Kalau menurut saya, jadi nanti kalau bisa ya, yang belum aktif ya dicoba lagi gitu, gimana caranya bisa aktif karena ini sebenarnya training ini harus digunakan oleh teman-teman itu untuk memperluas networking gitu. Nah, itu kan ada beberapa orang trainer. Terus jadi sesudah ini jangan berhenti sampai di sini gitu. Bisa kontak-kontak juga apa yang ini mungkin ada pertanyaan atau diskusi atau dijadikan tempat untuk saling berbagi pengetahuan. Mereka juga sangat ingin kita ekspornya bersama. Sebenarnya inginnya mutual pokoknya mutual beneficiary untuk masing-masing gitu. Indonesia dapat apa, USGS dapat apa, sebenarnya itu. Tapi intinya kan bagi kepentingan ilmu pengetahuan dunia gitu ya. Kita juga nggak boleh toh data juga mereka sudah punya gitu. Kalau dilengkapi dengan data Indonesia kan itu mungkin kalau ada puzzle gitu itu mungkin kita bisa menemukan puzzle yang belum lengkap dari sisi ilmu geofisika tentang Indonesia kalau saya gitu. Gitu ya. Semangat ya teman-teman ya. Karena ini susah karena kita nggak bisa interaksi langsung jadi gimana kayaknya senyap gitu ya. Jadi memang akan lebih baik kalau bisa langsung gitu kan. Tapi ya karena virtual juga, tapi harusnya ini nggak ada training, jadi ada training gitu kan. Biasanya orang pusat tuh kalau yang training karena ngundang dari daerah biayanya mahal seperti itu. Jadi kan ini lumayan gitu. Itu aja sih yang mau saya ini kan sebelum teman-teman ikut lagi nanti. Mudah-mudahan tetap semangat. Saya mau dengar suara dari Papua dong. Papua nanti sama yang paling ujung ya. Jadi dari Aceh dan Papua aja lah mewakili teman-teman.
Selamat pagi, Bu.
Iya, selamat pagi.
Ya, Bu.
Pak Dedi ya.
Iya, Pak.
Kurang jelas suaranya, Pak.
Oh, pakai PC, Bu. Pakai PC, Bu. Halo, Bu.
Oke, iya silakan, Pak. Masih samar-samar tapi nggak apa-apa.
Selamat pagi, Bu.
Pagi, Bapak.
Good morning, Nelly.
Hi, Walter. Kan udah datang nih. Hi, Walter. I just want to have a small discussion first before we start.
Okay.
Okay, thank you, Walter.
Yep.
Rajin dia udah datang. Gitu ya. Ada yang mau disampaikan, Pak, dari Papua?
Iya, Bu. Mungkin nanti kalau untuk kedepannya kan kita nggak sampai putus di sini, Bu.
Kenapa, Pak?
Untuk kedepannya kan kita nggak sampai putus di sini, Bu. Ibaratnya kan masih ada kelanjutan lagi. Mungkin nanti bisa di-sharing kontak-kontak dari lecture-nya, Bu. Gitu, Bu.
Iya, boleh silakan aja, Pak. Itu tidak. Yang penting mungkin saya di sisi supaya saya tahu kalau berkenan. Kalau enggak juga nggak apa-apa.
Siap, Ibu.
Iya. Mungkin dari Aceh ada. Saya lahir di Aceh soalnya. Aceh ada kan ya? Stasiun geofisikanya ada? Belum hadir atau bagaimana?
Ada dua kalau nggak salah, Aceh besar sama Aceh.
Belum hadir lah barangkali ya. Satu lagi lah, dari mana tuh? Dari apa ya? Ternate. Oh, nggak ada juga. Kalau nggak ada lah ya? Nggak ada ya? Ternate belum hadir. Aceh belum hadir.
Ternate ada, Ternate. Hermijal.
Mana? Ada yang mau diiniin nggak dari Ternate? Ini perempuannya berapa persen ya?
Lebih banyak laki-lakinya sih, Bu. Perempuannya cuman beberapa gitu, Bu.
Sedikit ya?
Sedikit, nggak terlalu banyak, Bu.
Yeah.
Cuman pengajarnya perempuan semua kayaknya.
Kayaknya sudah salah kita ini. Pengajarnya perempuan loh.
Rata-rata perempuan.
Kita jarang ya. Tapi nggak apa-apa. Sedikit tetapi powerful itu nggak apa-apa. Nanti mudah-mudahan yang perempuan itu banyak yang aktif dan bertanya. Kalau saya catat semua yang bertanya. Apa pertanyaannya? Karena itu penting. Karena itu mungkin itu yang harus kita lakukan next-nya. Mungkin gitu aja ya. Ini udah berapa menit lagi? Kalau nggak ada, soalnya besok udah penutupan gitu. Di sini nggak ada acara apa ya Mbak Dona ya? Nggak ada acara apa gitu. Cuman training gitu ya. Apa gitu nggak ada ya? Saya nggak tahu ice breaking-nya kalau virtual begini. Ada nggak ya?
Senang kayak gitu mungkin, Bu. Tapi
nggak sempet ya?
Takutnya waktunya, Bu. Mereka kan malam sekali. Khawatirnya di situ kalau misalnya kita selipkan ice breaking kan ice breaking cukup lumayan banyak, Bu. Taruhlah 5 menit, Bu ya.
Oh iya.
Jadi, khawatir nanti terpakai, sedangkan yang nggak pakai ice breaking aja kayaknya waktunya udah ngepas banget gitu ya.
Ngepas ya. Ya udahlah nanti mungkin setelah ini ya. bisa ketemu-ketemu lagi supaya makin solid gitu. Itu aja dari saya. Makasih ya teman-teman. Mudah-mudahan hari ini bisa aktif ya. Bisa banyak pertanyaan itu bagus. Ini juga bagi mereka juga kan itu berarti masukan. Dan bagi kita berarti oh iya itu belum dilakukan dan itu harus dilakukan. Itu aja. Makasih teman-teman. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Ya.
Masih ada 7 menit silakan. Mau
Kita mulai
sarapan.
Bu Nelly ya.
Tunggu aja jam 8.
Kita kemarin cepat-cepat dulu. Biar ternyata emang walaupun pagi
Oh enggak
juga.
nunggu jam 8. Oh iya kalau dia udah ada bilang aja bisa dimulai kali atau apa. Silakan aja saya ini.
Ya, terima kasih Bu Nelly. Yeah, hello Walter. Good morning and good evening. Yeah, we have 7 minutes. We will start or wait. Still wait someone.
Yeah, so of course. Very good. That's fine. 7 minutes, that's fine. Okay. And you will give the post exam tomorrow,
Yes. Oh yeah.
Thursday,
Yes.
or today.
This afternoon, Walter.
This afternoon. This
Yes,
afternoon, yeah.
For you, yeah, tomorrow.
Bu Nelly, mohon mungkin tadi hasil itunya sudah saya kirim ya Bu ya. Yang hasil
Apa
dari
nggak jelas Mbak Dona, nggak jelas suaranya?
hasil dari
oh iya.
nanti tolong sampaikan ke Walter Bu ya.
Oh. Walter, do you want to I want to share you the result of the pre-exam.
Yeah, I want to see.
Okay, I will send you through email right now.
Yeah, okay. The exam is difficult.
Yes.
Not so easy.
Yes.
Average score maybe 60%.
Yeah. You can guess.
Because many difficult questions.
Yeah, I think because this is the new knowledge maybe, so it's very difficult.
So they have the opportunity to learn many new things. That's okay.
Yeah, maybe the mostly a question of the pretest related to geologists. Yeah, I think because almost participant in here mostly the background study like as a seismologist.
Of course, yeah.
So different specialization.
So difficult to answer the question about geology.
Yeah.
Yeah, that's okay. What was the highest score? Highest score was 80%?
Yeah. As I remember, yeah.
Ya, Harpan kita mulai aja Harpan ya. Okay. Walter, maybe we can start.
Of course, we can start. Let's go. Very good.
Yeah. Thank you very much for your. Thank you very much for our speaker. Thank you very much for your speaker and Walter in here. Good morning and good evening, everyone. Yes, and actually, I say thank you very much for our participants who are loyal to join this training until this training ends. And this is the fourth day of the training. So I hope you are always enjoy and happy and enthusiastic in undergoing in this training. So maybe we have a single moderator for today. Yeah, welcome to Harfan, Muhammad Harfan. Muhammad Harfan, he is from Earthquake and Tsunami Center, especially in the subdivision of tsunami mitigation. Maybe please pay attention for the time because we have the limited time, so we have to strict about time. Go ahead, please, Harfan. Time is yours.
Okay, thank you, Ms. Maduna. Good morning, speakers and participants. Is my voice clear?
Yeah, it's clear.
Very clear,
Okay,
very
great.
clear. We hear you
Okay,
nicely.
great. Yes, my name is Harfan and I will accompany you for current lecturing session. Okay, so for today's session, we'll have two lectures. The first lecture will be talk about the climate and hazard and will be presented by Miss Ashton Woods. And the second is about volcanoes and earthquake and will be presented by Miss Hale Putra. Okay, the rule is still the same like yesterday. The speaker will have 40 minutes to deliver their presentation and then will be continued by 10-minute discussion session. And for all the participants during the presentation, you may post your question in the chat box and I will read it for you later in the discussion session. Okay, for the first lecture, Ms. Woods, are you ready to start?
Hello, yes, I am ready to start. Thank you. And good morning, everyone.
Okay, you ready?
Yes. So.
Okay, great. Okay, then without further ado, Ms. Woods, the time is yours.
Thank you so very much. Good morning, everyone. My name is Ashton Woods. I presented on day 2. I'm a U.S. GS geologist with Menlo Park, California, the Earthquake Science Center, and I'm doing climate change impacts on natural hazards, part 1 today. So give me a moment to share my screen and then we'll get started. Can everyone see it okay? So let's get started. Lecture 14, Climate and Hazards, Part 1. There are some common misconceptions surrounding climate change. Most people believe that it's synonymous directly with global warming, but this is simply just one mechanism of climate change. It's not just global warming, it goes into desertification, the frequency and intensity of natural disasters, ocean acidification, public health issues, and anthropogenic impacts. We are able to trace that current climate projections that we are experiencing now are similar to that during the Holocene climatic optimums 9,000 to 5,000 years ago, where it wasn't as, it's not as hot as warm house Earth. We are still technically within the ice house stage following the last ice age, but it's still significant enough that we'll start to see different variations of weather frequency and intensity, as well as disasters occurring, dealing with drought-related conditions and dealing with ocean rise, solidification, and temperature changes. We can see further evidence of this on this chart here, looking in the global averages of climate change, comparing temperatures increased in Celsius to sea level rise in millimeters, showing that in 1995 all the way to 2020, we have been rapidly increasing. Several indicators dealing with climate change are pollution, the manifestation of more diseases that are uncontrollable, storm intensity, wet, dry season variability, and unpredictable weather, and drought-related conditions leading to crop failures. and leading to permeability of soils and vulnerability of soils. Mechanisms of climate change that we're going to discuss during part 1 deal mostly with the atmospheric changes. And we'll be looking into global cooling, the increase of UV radiation, and ozone destruction, and how this all plays a part into creating storm intensity and storm unpredictability. So in the gray circle on the bottom of this diagram, we have the halogen gases, which include bromomethane, which is normally released during pesticides. Halogen gases are normally released due to anthropogenic causes, and anthropogenic simply just means human involvement and human interaction. On the right-hand side, the green circle deals with the greenhouse gases, natural gases, CO2, CH4, methane, nitrogen dioxide. The one that I want to focus on for this diagram, however, is the center gas, which is hydrochlorofluorocarbons, which is when chlorofluorocarbons and hydrofluorocarbons combine together and create an ozone depleting gas that causes cooling and seasonal variability in areas where there's high concentrations of this. So here we're looking at the daily max ozone for July 27th of 2020. The scale at the bottom is in parts per 100 million, but I'm going to reference it as parts per million. And we can see here on the chart that the red areas are the slightly more elevated zones and the blue areas are within acceptable safe zones. The global accepted average for ozone is about 0.10 parts per million over an 8-hour period. So it's well within the safety here with the 0.1 parts per 100 million and the 0.2 parts per 100 million, as those are 0.01 parts per million. As we get more towards the red part of the scale, as we see over the Himalayas between India and China, we see that there's more of a susceptibility here of the ozone layer having significant drawbacks. We can see this further looking into July 29th to July 30th, 2020 data on the ozone thickness. This is recorded in Dobson units, and again, global accepted range is about 300 Dobson units for ozone layer thickness. Again, we're starting to see that along the equator and the southern hemisphere, there is some safety with it. The higher levels of the Dobson units here for this scale aren't a significant problem in comparison to if they were lower than the 300 scale, as anything below 300 Dobson units results in the tearing in the ozone layer. The ozone layer, and the ozone gases, when they mix with nitrogen dioxide, this can cause storms to intensify rapidly without significant warning, especially storms that form over the ocean during typhoon season. Here we're looking at the daily max of NO2 again for July 27th, 2020. This one is measured in parts per billion, and we can see that Indonesia and several of the other countries in the southern hemisphere and along the equator are still in relatively safe zones. NO2 toxicity is between 100 to 150 parts per billion. So it's actually interesting to note that on this image, we see that Greenland is actually within the dangerous levels of early NO2 toxicity. The more toxicity caused by NO2, the more likely that asthma and emphysema and other lung and respiratory related conditions can occur. So this is, Greenland was having a very serious issue. I want to transition into a different mechanism now that we've covered some of the basic gases and go straight into the deforestation of tropical swamps and how they deal with sediment transport and how sediment transport can cause changes in storm and disaster-related frequency and intensity. Here we're looking at an unspecified region in the Kalimantan on the island of Borneo. On the left-hand side, we can see that there is a brown patch where there's some evidence of desertification beginning to occur. But I'm going to focus on the CO2 emissions primarily during this lecture for the peatlands in Indonesia. The CO2 emissions from peatland degradation chart that we see here covers information that was originally collected in 2009, but has been updated for 2017 projections, and shows that the majority of global emissions of CO2 do arrive from peatland related implications such as fires and degradation of peatlands, as well as the removal of peatlands, contributing to up to about 200 million tons of CO2 emissions annually. This happens because the peatlands are a natural sink for carbon. They compress all the carbon beneath the ground layer. Here in the diagram, we show on the bottom that here's an example of healthy peatlands where methane is just being released from some of the decaying organic matter in the peatlands, but the carbon is remaining below the surface, and there's an equal level of exchange between the vegetation and the soils and CO2 levels. On the top, we see draining peatlands as water is being removed from the peatlands due to irrigation, drought-related conditions. This can cause carbon and methane sinks to develop, which allows for more CO2 and methane to be released into the atmosphere within these areas. And then same thing here on the top, we see the implication of fires in drained peatlands, showing that there's a significant increase in the amount of methane and CO2 being released, and that the fires are able to travel through the carbon sinks below the surface of the peatlands and travel and just stay lit underneath the surface levels for several days, weeks, and even months after the initial fire has started. We can see this further in the diagram that's provided here. In the scenario that fits this diagram, there's a village across from a tropical swamp that has been subjected to drought-like conditions, which has led to a peatland fire to emerge. As the peatland fire starts to die down, as we see over here, the fire escapes instead to beneath the surface levels and is traveling through the surface levels down into the other deposits of peat where the carbon is high and the oxygen is being introduced through the permeability and the exposed areas of where the fires have occurred. So the fires can travel down and say about a week has passed, the fires are still burning, and then about a month later, the fires have burned their way through. And because people within an urbanized area are constantly doing city planning work, they're constantly making changes. Something as simple as making a new well can allow for the fires to exit up to the top of the surface where there's more oxygen to burn off. And that causes the village to now be on fire a month after the initial fire has taken place. Here we look at CO2 fluxes along Indonesia and Japan, as well as Papua New Guinea. We can see from the chart at the bottom, or the legend for the map at the bottom, the size of the circle represents how much CO2 flux is being released in tons per day. And the lines of color, as well as the circles, represent the amount of carbon dioxide per sediment transfer that is happening, as well as the weight percentage of sediment CO2 that contributes to the emission value. Though there's a large amount of it happening here in Papua New Guinea, it's also important to note that the islands, the trailing islands and the islands of Java, as well as for Sumatra, there is some significant amount of CO2 being released from the sediments due to storm-related, drought-related, or fire-related conditions that allow for the peatlands to be damaged and release up to most over 2,500 tons of CO2 per day. Carbon dioxide is not the only thing that's released during these fires. Formaldehyde is also very significant. We see at the end of 2019 and the beginning of 2020 that there is a formaldehyde peak. This was due to the fires that followed after September of 2019 in certain parts of Indonesia that resulted in agroforestry areas to be burned, and the burning fertilizer released this formaldehyde into the atmosphere. Formaldehyde is a particularly damaging gas to the ozone layer. However, observing information from July 29th and July 30th of 2020, we see that there isn't as much significance in formaldehyde levels. And I know it's a significant jump from the previous chart that looked in the 2019 to 2020, showing that the peak had risen up at the end of 2019 and to the beginning of 2020 and then declined. Normally, formaldehyde can last within the atmosphere for several months, depending on the location of where it is at. Here in Indonesia, there's some slight emissions, but nothing too significant. And the reason why Indonesia doesn't have as much formaldehyde within their atmosphere contributing to the seasonal variations of wet and dry seasons and causing drought conditions and causing an upset in the equilibrium of atmospheric gases is because of UV. So the UV index is a particularly high index level for Indonesia. The chart or the scale at the bottom, 16 is extremely dangerous levels, whereas 0 is the safer levels of UV radiation. The UV radiation is good at destroying formaldehyde in the atmosphere, but more exposure of UV radiation can cause the vegetation in the areas where the UV index is high to not produce, basically not to maintain health. And when vegetation dies off, that causes the soils to become more vulnerable. And so things like seismic activity, droughts, fires, different types of flooding events become way more susceptible in these areas where the vegetation has died off. I'm going to transition now into an additional mechanism that Indonesia faces dealing with atmospheric gases, which is the emission of volcanic eruptions. Here we look at Himawari satellite image of a Krakatoa eruption in 2018 in the Sunda Strait. It's showing in clean infrared window at band 13, basically showing how much sulfur dioxide and other gases are being released into the atmosphere and the extreme temperatures that are causing the atmosphere to almost seem as if it's being ignited around this area. This is also the same eruption, but showing it in red visible and band 3. So that way you can see that there was some significant interference with atmospheric gases that caused some serious meteorological conditions to occur later because of the changes in the atmosphere and the cloud cover that followed after this eruption. We also can track the 2018 and 2019 and 2020 sulfur dioxide peaks that followed during several volcanic eruptions during Indonesia. Volcanic smog is particularly damaging for Indonesia and has caused some serious issues with the equilibrium in the atmosphere over Indonesia. And so drought conditions have been occurring more frequently for Indonesia because there hasn't been enough sulfur dioxide being removed from the atmosphere following these volcanic eruptions. the extreme peak that we see at the end of 2019 and at the beginning of 2020 is following the eruptions along the Ring of Fire, particularly along the several different volcanic eruptions that happened at the beginning of the year for Indonesia, and has since declined as we progress throughout the year. However, even with all the volcanic activity that is happening, the SO2 levels are still significantly lower. The scale here is in Dobson units, and there isn't a majority of SO2 over Indonesia as there is in, say, places like South America, North America, and in Australia. And the reason why is because the majority of the SO2 in Indonesia is being absorbed into the ocean, which goes into an additional mechanism of climate change, the acidification of coastal waters, because the SO2 is being absorbed into the coastal waters and the marine waters, and it's also being absorbed into well-drained soils along the coastline. We are seeing more trends of acidification occurring along the coastal regions of Indonesia, causing destruction of natural barriers such as mangroves and coral reefs that help to provide protection during high tide and tsunami related incidences, as well as typhoon related weather. Acidification happens when CO2 is mixing with other gases such as the formaldehyde, the sulfur dioxide, as well as things like cyanide and carbon monoxide. These things can't properly mix within the marine coastal waters, and if too much of it enters in, it causes damage to healthy marine biomes over time. And it causes free hydrogen ions to escape that also lower the level of healthy microbiomes within the coastal waters. And then the pH level steadily increases over time with the more introduction of various chemicals and gases. These gases come together to create exposure to sea surface temperature rise following acidification, causing even more damage to coastal barriers and causing more sediment along the coastline to become more susceptible to being pulled out into the ocean, as well as issues with rising sea levels. Storm intensity tends to increase, disaster resiliency drops for coastal regions because of these sorts of implications, because of the lack of natural barriers. There's more susceptibility to the coastal areas of Indonesia experiencing more significant damage following disaster-related events, particularly dealing with flooding and tsunami-related events in the future. This chart on the right-hand side is showing the averages over a 20-year period for each day of a year. It's measured in Kelvin, and it's representing the climatic sea surface temperature changes, showing that Indonesia hasn't had any significant sea surface changes for temperature within the past 20 years, except that maybe it's starting to elevate higher than what it would normally have experienced, say if we had looked at data 30 or 40 years ago. I briefly want to cover this with you all, because again, this goes into one of the reasons why there is so much coastal vulnerability for Indonesia. The protected marine ecoregions are represented by the scale on the left-hand side in percentage of protected levels. The purple areas represent areas where there is very little initiative to protect these marine ecoregions. So no one is really focusing hazard mitigation and disaster mitigation tactics to address the removal of or the dying off of mangrove forests, or looking into the removal of sandbars or damage to the coral reefs that add to additional protection during high tide related events and wave related flooding. We see in the green areas that there is a higher level of percentage of protection for these ecoregions, mostly on the coastlines of Papua and along the trailing islands of Java, including Timor. Here I've highlighted on the same map, but in grayscale, we have the blue and red regions. Blue regions are areas where flood resiliency is capable of occurring, but there's still much need for improvement. There aren't enough mitigation policies dealing with coastal flooding related events and the protection of these ecoregions to help with that. So that's the reason why they are still vulnerable. The circles represent flood resiliency. Because the ecoregions have been protected, there's less flooding potential in these areas. And then the high flood risk areas are actually along the the opposite coastline near the Indian Ocean for Sumatra and Indonesia, where if any sort of storm impact or tsunami related incident occurs, these areas are extremely vulnerable to damages occurring. This also points out the Sunda Strait, which I mentioned previously when dealing with volcanoes, and then I'm about to also continue into following this. Now I want to go into meteotsunamis. Meteotsunamis are a type of natural hazard that is present whenever there's gravitational forces or barometric pressure changes that are happening during high tide events. They can become flood-related disasters when these gravitational forces, say like the moon is slightly closer to the earth than expected, or if there's a sudden change within the barometric pressure over that given area. The wave generation happens and it causes these floods to occur, and there's no proper way to predict how and when these meteotsunamis will hit the coastline. But once they do contribute to a significant amount of flooding. Here I have a quick video covering more about meteotsunamis. It's a simulation. However, last time when I presented, I had issues with the sound quality. So I'm going to try to pull it up on YouTube. I have it prepared already. So hopefully you all will be able to hear it. And if not, please message in the chat and I will move forward. Okay, so I've been informed that there's still no audio. I apologize for that. If you want to see this video that covers more into the mechanics and how meteotsunamis happen, please feel free to review the recorded lecture as there will be sound for the audio there. I apologize that I'm having issues with my videos. I don't quite understand why it's doing that. But I'm going to move forward. As I pointed out on the ecological map in vulnerable areas, the Sunda Strait was a particularly vulnerable area and still is. This is reviewing what happened during the 2018 Anak Krakatoa eruption. We know that there was some conflicting data for Indonesia from several different stations along the southern coastline and of Sumatra and the western coastline of Java, where people weren't able to properly convey whether tsunami related events were happening following the days after the eruption and dealing with the underwater landslide that occurred in this area. However, I do want to point out that there was evidence of a meteotsunami that occurred during this time on top of a high tide warning where the high tides were already at a 2-meter height. And we see that here on this diagram, on this map, highlighted in red, where the high tide warning events had occurred, showing that there was the potential for tsunami conditions and flooding to occur within these areas following the eruption before wave generation happened with the underwater landslide. This is just a quick visualization of tsunami generation on top of the 2-meter wave that occurred, as projected based off of data from the Banten station and the Serang station. Again, there's much controversy about whether or not there was tsunami wave generation. There were some people who reported that parts of the western coastline of Java barely had any flooding, and there were other areas south, to the south of the western border that expressed that there were waves that reached as high as 16 feet and caused significant damage. There's still a lot of study that's going into it, and this has been a particular interest for me, so very excited to have brought it up during this lecture. But now I would like to start transitioning to the conclusion by going into the vulnerability of Indonesia in comparison with 2 other countries, dealing with climate change impact and CO2 emissions by country with compliance to the Paris Climate Agreement. Here I've chosen Japan and Samoa as comparative. The circle sizes represent GDP reserved for climate-related impacts and disaster resiliency policies. And the colors are mentioned in the scale on the right-hand side, where red is highly insufficient and green is extremely sufficient in compliance to the Paris Climate Agreement. For Japan, it's actually very interesting because it's considered partially sufficient in compliance for dealing with climate vulnerability and disaster vulnerability due to climate changes. However, the reason why it's interesting is because if we look along the X and the Y axis, Japan is particularly close to the area on the x-axis where there is indication of high levels of CO2, and Japan is actually known as one of the largest contributing global CO2 emissions in the entire world. Then we have Samoa on the left-hand side, which produces very little CO2 emission, but is considered in the red and has very little GDP reserved over for disaster resiliency. We're going to investigate into each of these countries further before the end of this presentation. For the global ranking of Indonesia, we look into the INDI-GAIN country index, which looks at a review of 170 different countries. The scale for the rank goes from 170 being the most vulnerable to 1 being the most prepared and the least vulnerability for climate-related impacts contributing to disaster-related events. Indonesia is number 97, so it's not entirely the best score. The vulnerability is relatively high and there isn't as much readiness in the policies to protect against climate impacts dealing with disaster mitigation techniques and disaster resiliency. However, we do see that from the year of 1995 at the bottom of this diagram to 2018, the score has been decreasing from 121 to 97, which means that Indonesia is experiencing improvement and is starting to take into consideration more about climate change and its relation to disaster generation. When we look at Japan, this is where the most shocking data is. Japan is north in Pacific Ocean. Its ranking in 95 was 16, and it has gone up and down only a few points to 2018 standards at a rank of 15. This is shocking because, again, Japan is known as the main CO2 emitter for global CO2 emissions. and yet their vulnerability rating is lower than Indonesia, dealing with climate-related impacts for disasters, and their readiness for dealing with these disaster-related events is relatively high. And then we go into Samoa, which is also within the Pacific Ocean. It's interesting to note that Samoa is actually one rank behind Indonesia. And instead of decreasing in score from 1995 to 2018, they've actually been increasing in score. The reason for this is a closer inspection of Samoa goes into the fact that most of their coastal areas are not being well managed, and the tropical areas where there are natural carbon deposits are being removed to increase tourism, as well as the use of more greenhouse gas energy to allow for more modernization of Samoa, which is why their score has been increasing, which means that their vulnerability is becoming significantly higher than what their geographical area can handle. And so that is the reason that they're ranked behind Indonesia. And this covers part 1 of climate change impacts, dealing with natural hazards. Thank you all for your attention.
Okay, that was great.
Okay.
I think the moderator will take over.
Okay. Thank you, Ms. Woods, for the presentation. Okay. Let me summarize a little bit about the previous presentation. The previous presentation is talk about the climate change hazard, and some of the climate change hazard is global warming. And global warming has a mechanism like atmospheric changing, increase in UV radiation, ozone destruction, and storm unpredictability. Some of the cause of the climate change is natural causes like volcanic activity, but some of the cause, including an anthropogenic cause, which means it's caused by human activity. Human activity that involved in global warming, for example, is like deforestation. This human activity increase the greenhouse gas emission like nitrogen dioxide, sulfur dioxide, carbon dioxide, and etc. And this increase of greenhouse gas may lead to natural disasters to occur more often, like more land fire, more flood, and more intense storm. And also this may cause the damage to ecosystem, for example, like the damage to natural reef due to the ocean acidification, and also may lead to the occurrence of respiratory disease. And Indonesia is quite vulnerable to climate change due to its carbon dioxide emission and highly insufficient policy to mitigate the increase of resiliency to the climate change. Unlike Japan that has more CO2 emission but has low vulnerability because the policy is quite effective to counter the problem. But the recent data show that Indonesia has shown a little bit improvement. Okay, maybe anyone has any question?
Yeah.
Regarding the previous topic? Okay,
I have
please.
question.
Okay, please.
Yeah. Okay, thank you for your presentation. Very informative, and I want to ask a few questions. The first, regarding global warming, what's about some natural factors such as the occurred volcanic eruption? How is the analysis about it? And the second, can we assume that global warming is just a natural process? And the third, how are the consequences of US leaving the Paris Agreement? Thank you.
Hello,
I
Ms.
didn't
Woods.
hear Ms. Woods.
Ms. Woods, please unmute your speaker.
My apologies. Those were wonderful questions. So dealing with the implication of global warming and as a indicator, as a driver of climate change, because as I mentioned in the lecture, it's not synonymous with climate change itself. It's just one of the few drivers for why climate change or what climate change can result in, and what is contributing to climate change. Climate change is a natural process. We see that there are many historical, there's much historical evidence in the paleoclimate that investigates into similarities of our current climate with the climate within the Holocene before the medieval era. And this is because we are within the icehouse state. Icehouse state just means that we still have glaciers present on the planet. It's following the last glaciation period. We are able to see that even though the temperature levels are rising higher and we're not used to it, it's not significant enough to reach warm house state. And a warm house state, which was experienced during the Eocene, is the actual absence of any sort of ice on the surface, no glaciation. The temperatures were much higher, significantly higher. And so we can safely assume that climate change is something that does naturally occur in the Earth processes and can have extreme variations of being extremely hot to extremely cold due to mass glaciation, mass cooling, and then mass heating of the planet. The issue that we need to address when dealing with climate change now really is dealing with disaster resiliency and developing new technologies to help combat against the unpredictable and frequent occurrence of storms and natural hazards developing into disasters. So when we actually look into the climate data, we're able to see that the disasters are happening more because of these variations in our current climate, because we haven't properly mitigated for them before they became a problem. Natural disasters happen because there has to be an at-risk affected population. Otherwise, they're just natural hazards. They are always ever present. They're always occurring. A landslide could happen in the middle of a heavily forested area where there's no people, and that's not considered a disaster. That's just a natural process. And whether it's been created by climate change variations or due to either drought or flood related issues because the climate has changed within that geographic area, it's still considered a hazard until that landslide or additional disaster related incidences affect a population. So that's the reason why it's important to look into global initiatives like the Paris Climate Agreement. I was very sad when the United States pulled out of the climate agreement, which I believe is another question that you asked, was an analysis of what I thought about the US not being part of the Paris Climate Agreement. It is rather unfortunate that we have opted out as a country for that. However, that doesn't mean that global initiatives in the future will have the same resistance that the United States provided before. And there are still several policies and global initiatives that the United States is still following, like the Kyoto Protocol, that help us to determine how to properly mitigate against these climate variations. So I hope that was enough to answer all of your questions that you asked.
Yeah, a little bit about technical analysis from volcanic eruption.
Mhm.
Really.
Oh, yes. And so we're able to measure that through in-field investigation as well as looking into historical data of previous volcanic eruptions. We could do this through soil sediment cores and looking into rock facies around those areas to figure out how much of the concentration of volcanic gases has permeated into well-drained soils and have been absorbed in the well-drained soils and have just been consolidated over time. We're also able to measure that by just using atmospheric measurements, things that look into the interaction of like acid rain happening following a volcanic eruption and measuring the amount of sulfur dioxide levels and other chemicals within acid rain to figure out like how much of it has been emitted into the atmosphere should that fall, or just again doing in-field observations. So there's several different ways of analyzing this information. The one that I used for this presentation today looked into a combination of satellite data in comparison with in-field collection methods, dealing with atmospheric collection methods and looking into the possibility of acid rain events following the eruptions that have occurred in Indonesia between 2016 to 2020. And that was the chart that I used today.
We have some questions in the chat box.
Yes. Okay. For the next question, is already in the chat box. It's from Mr. Eshad Octav of Gerontology Physics Station. There's two questions. The first question is, based on your presentation, why southern and little central part of China have a higher solar UV index than Indonesia, even though it's located at higher latitude than Indonesia? And the second question is, are seawater pollution such as garbage or waste dumped into the sea can increase the probability of acidification of coastal water?
Yes. Also more good questions. So the reason why the southern and central parts of China have higher solar radiation is actually something that I also kind of cover in the part 2 of the climate change impacts and natural hazards. And that's because there are additional forces at play that allow for the atmospheric gases to be out of equilibrium, and they allow for more absorption of solar radiation within those areas, as well as the high amount of snowfall that's along the Himalayas and things like that. One of these contributions to UV being more like available in China is the presence of harmful algae blooms. This can happen on it doesn't just happen in marine waters, it can happen in natural lakes, and it can also happen on snowmelt. And when these harmful algae blooms happen, they release more CO2 into the atmosphere. They cause the light to scatter because it's not able to penetrate past the actual hab itself. And once it actually decays, it releases extreme levels of methane into the atmosphere, which can cause the air in the atmosphere to be more vulnerable to UV radiation permeating through in those areas. And China had a very significant level of harmful algae blooms that were occurring during that time. As far as seawater pollution from garbage and waste dump, this is actually really important to also go into. Eutrophication is a huge problem, dealing with nutrient runoff, as well as improper debris disposal and wastewater and stormwater. They all contribute to acidification along the coastal waters. I just didn't cover that for part 1 of this lecture, but I briefly go into that for part 2.
Okay,
which I will present tomorrow.
Okay, we still have about 4 minutes for the discussion session. Is there any question?
Hello.
Hello.
Okay, please, Mr. Relly.
Yes. Hello, Aston. My name is Relly from STMKG. So thank you for this opportunity to ask question. Several years ago, Indonesia faced with huge forest fires cases, and we also sent the smoke to our neighbor countries such as Malaysia and also Singapore. And this year, I saw in CNN, United States also has the similar problem. There is huge cases for forest fire. So my question is, how United States deal with this problem, and also what's the mitigation scenario for that? Thank you.
Yes, of course. So dealing with the chemical gases that are released from burning fertilizers in these areas, as well as dealing with natural gases that are being released from the carbon and other sediments that are subjected to these forest fires, as well as just the cyanide and ammonia and carbon monoxide that's released when fires happen to begin with. All of these are things that we have several different agencies in the United States handle. The National Park Service works in collaboration with the USGS, as well as in collaboration with the Federal Emergency Management Agency to track fire-related zones and to help prevent fires from breaking out in these areas by going through investigating the soil profiles, making sure that if there's any sort of urbanization that might be occurring in areas where high fire susceptibility is diminished or is following proper fire resistant codes. So the majority of what we do for mitigating against fire damage is primarily in policy and field investigations. When the fire itself actually happens, we have some significant issues dealing with mitigating during the actual fire event. We can see this as we see this as a problem in the United States, particularly in California and in areas of New Mexico, and even sometimes in Nevada, where the fires get so out of control because there's just the perfect conditions for fires to burn. One of the mitigation tactics that's discussed with the United Nations is they talk about the separation of housing. So instead of creating consolidated areas near areas where peatland may be, or where brush and dry vegetation might be, it's better to actually space out those areas from urbanized areas. And when you create a new city or when you expand onto a city, instead of keeping the buildings so closely near each other, to actually also expand them out from each other as well. So that way when fires do happen, it doesn't just raise the entire area. Also looking into the soil moisture content of the sediment within areas where fire events have occurred throughout history as well as in more recent years helps to create even better mitigation techniques and policies to follow up with that. What was the second question that you asked as well, please?
Just only one question. Yes.
Yeah. Oh, okay. All right.
Okay.
But I hope
Okay,
that
for the
was
last question, yeah.
good.
Okay.
Okay.
Okay, thank you.
Thank
Okay.
you.
Okay, thank you, Ms. Woods. I think I'm afraid that the time is up, and I see that there is still one more question. I will collect the question and will post it to you, Ms. Asatun. Is that okay with you? For you
Yes.
to answer it later.
I can also answer it in the chat later as well when we
Okay.
go towards break, and I'll make sure to connect it to the person who asked the question if you would like. I can also put it in a Word document and send it like I did on day 2.
Okay, that's great. So for all the person, if you still has any question to Miss Woods, you may post your question in the chat box and she will answer it later. Okay. So I think the time is up. Thank you, Miss Woods, for your great presentation. Please give big applause.
Thank you all so very much. I am enjoying my time lecturing and teaching with you all, and I'm excited for the training to continue. So.
Okay, same with us. Okay, so we'll go directly to our next lecture. We'll learn about the volcanoes and earthquake, and will be presented by Miss Hale Putra. Miss Hale Putra, are you ready to present your presentation?
Yeah, I am.
Okay, great. So, Miss Hale Putra, please, the time is yours.
Okie dokie. Let me find my PowerPoint. So I guess this is the first time you're seeing me live because my last presentation that was on day 1, you saw me over a recording. So I guess I have to introduce myself. So I am Hallie Pitera. I am a geologist with the Earthquake Science Center based in Menlo Park, California for the United States Geological Survey. And some of my interests and past research revolve around tectonics, a lot of petrology, and sometimes structural geology. But today I am pleased to presenting lecture 15, which is on volcanoes, earthquakes, and volcanic hazards. So we will jump right into that. So by now you've become very familiar with this map. You've seen it on all of our intro slides. You've seen it in a tectonic context. You've seen it in a seismic context. You've seen it in regards to other hazards. But for this lecture, we're going to be looking at it in a volcanic context. So we're going to be focusing on all the little red triangles all over this map, which are our volcanoes. So Indonesia has 147 volcanoes, with 76 of those volcanoes being active. So just over half are active volcanoes. And you'll notice that a lot of these volcanoes are parallel with their respective subduction trench. So these are all subduction related volcanoes. So one arc you can see sort of extends from the tip of Sumatra, follows the Sunda Java Trench, and extends all the way sort of through the Banda Arc over here. And these are generated due to the dehydration, partial melting of the descending slab. Magma rises up and boom, you got a volcano. And then we also have another group of volcanoes over here near Halmahera. Again, subduction initiated, but this time due to the subduction of the Malacca Sea Plate to the east and to the west. You have also seen this seismic graph before. It was in my previous lecture number 4. And in that lecture, we looked at this in a tectonic context, so sort of looking at the relationship between where the deep earthquakes are versus the shallow earthquakes. So looking at where a slab is subducting and maybe what a slab looks like based off of seismic data. But now we can look at this seismic data and relate it to volcanic activity. So you notice that there are a lot of shallow earthquakes following that exact line of red triangles that we saw on our last map. And that's just to show that seismic data and volcanic activity are very much intertwined. In fact, one of the ways that we try to predict a volcanic eruption is by looking at seismic data. So usually before a volcano erupts, there will be what are called volcanic tremors or volcanic earthquakes. And this is just due to magma rising up through the surface. Sometimes the crust will expand. There will be a lot of tremors. And if we see a lot of tremors in very high frequency, this could mean that an eruption is imminent. Now, using this data, we can't exactly predict to the exact hour or even day a volcano will erupt. But it'll at least help us know when a volcano might erupt. So it could be months off, honestly. It depends. It's very hard to predict a volcanic eruption, just like it's very hard to predict an earthquake, just because these sort of things are very inaccurate. For geologic time, on that sort of scale, we can be relatively accurate, but for a day-to-day basis, it can be very difficult. But now we're going to sort of get into the meat of the presentation. So most of this presentation is going to focus on volcanic hazards, and then later on volcanoes that have had recent eruptions or have exhibited these hazards sort of as a spotlight. So I have no doubt that you have all heard these volcanic hazards before, but I'm just going to sort of go over them again, because they are very important to know, especially when sort of understanding a volcanic eruption and how to keep people safe from the effects of one. So first on our volcanic hazard list is tephra and ash. So you can have two types of volcanic eruptions. You can have a non-explosive eruption, or you can have an explosive eruption. So a non-explosive eruption sort of looks like maybe steam rising out of the top of a volcano, maybe some lava bubbling up towards the side. Sorry, my audio was being all weird. But you see a lot of non-explosive eruptions in places like Hawaii. But if you have an explosive volcanic eruption, which happens very frequently, all explosive volcanic eruptions will generate tephra, what is known as tephra. And tephra is fragments of rock that are produced when magma or rock is explosively ejected. So this is where you get your blocks, your bombs, your lapilli, And one of the categories for tephra is known as volcanic ash. So this is a projectile that is less than 2 millimeters in diameter. And because it's so small, volcanic ash is easily convected upward within a volcanic plume, and then can be carried downwind for very long distances. Eventually it will fall out of suspension and then could potentially affect communities and farmlands across hundreds or even thousands of square kilometers. So ashfall won't necessarily endanger human life unless you're out there breathing in the ash, in which case it can have severe effects on your respiratory system. But the volcanic ash can mostly endanger aviation and human infrastructure. So planes, you don't want to be flying a plane into an ash cloud. This ash cloud could be also very hot. So this could cause engine failure in the plane or damage the outside of the plane and cause it to crash. And then it also causes issues with human infrastructure. So it can clog up roads, maybe bridges. It can cover agricultural land or grazing land for animals. If there is enough ash to cover an entire grazing land for some livestock, the animals might starve. So there's a lot of associated hazards with tephra and ashfall. So when people usually think about a volcanic eruption, they might imagine lava spurting out of the top and sort of rushing down the side of the mountain and burrowing a nearby town. But that's not usually how a lava flow happens. Lava flows are very slow, and their dangerousness is sort of controlled by the type of magma that is erupting out of that volcano. So for instance, if you have a more fluid basalt flow, which is less silicious and therefore less viscous, this flow can extend for tens of kilometers from the eruption vent, and the leading edges of this flow can travel as fast as 10 kilometers per hour on steep slopes. However, if the basalt flow gets caught in a lava tube or creates a lava tube, this can preserve the heat of the flow better, and then the flow will be able to reach velocities greater than 30 kilometers an hour. However, if you have a more viscous andesite flow, these flows will only move a few kilometers per hour and rarely extend more than 8 kilometers from their vents. So you as a person can most likely easily move out of the way of an incoming lava flow. You won't necessarily be drowned in lava. However, everything in the path of an advancing lava flow will be knocked over, surrounded, buried, or ignited by the extremely hot temperature of that lava. So it can pose other dangers besides just immediately sort of killing someone in the way. It can also cause a lot of secondary hazards. So for instance, if lava erupts beneath a glacier or flows over snow and ice, the meltwater from the ice and snow can then result in a lahar, which we'll go over next, but that's a mud flow. If the lava enters into a body of water, or water somehow enters into a lava tube, then the water may boil violently, and you can cause sort of an explosive shower of molten material over a wide area. If the lava flow sort of flows over a lot of vegetation, this can produce methane gas. And then if somehow the lava and or methane gas migrates into a subsurface void and heats, this can cause an explosion. So there's a lot of different hazards that sort of come secondary to a lava flow. So our next hazard is a lahar. So I already previously mentioned this. A lahar is basically a mud flow. It's defined as a hot or cold mixture of water and rock fragments that flow down the slopes of a volcano and will typically enter into a river valley. If a lahar happens seasonally, it can also be known as a debris flow. So the important thing to note with lahars is that they can occur with or without a volcanic eruption. So an eruption may trigger a lahar by melting snow and ice, or by ejecting water from a crater lake. A pyroclastic flow can generate a lahar when the flow sort of clears out the area. So a pyroclastic flow is extremely hot and extremely destructive. So when it descends sort of down the slope of the mountain, it will clear off basically everything's path, all the vegetation and whatnot. And if this pyroclastic flow is then followed by severe or heavy rainfall, this can induce a lahar. But then they can also happen without the assistance of an eruption. So if you had an eruption a couple of years ago, or the side of a volcano is just sort of devoid of vegetation, and a heavy rainfall hits that sort of loose sediment that's sitting there, this can pretty much immediately trigger a lahar. But lahars are particularly, can cause serious economic and environmental damage to river valleys and floodplains specifically. So buildings and valuable land may be partially or completely buried by the lahar. It has the capability to destroy bridges and roads. And because of this, lahars can trap people in areas vulnerable to other hazardous volcanic activity, especially if the lahars leave fresh deposits that are too deep, too soft, or too hot to cross. So this is one of those hazards where evacuation is very important, because if a lahar happens to sweep through a town near a river, people can become trapped, and not only will they most likely starve because they can't cross the lahar, they are very vulnerable to then other volcanic hazards that may follow. So our next hazard is volcanic gases or volcanic volatiles. So magma contains dissolved gases, which will usually provide the driving force that causes most volcanic eruptions. But as the magma rises to the surface and the pressure decreases, these gases and or volatiles are then released into the atmosphere. And a lot of the time, these gases can be harmful to health, vegetation, and infrastructure. We're just going to go over a couple of the more dangerous gases that are released during a volcanic eruption. So first we have carbon dioxide, which Ashton sort of talked about, but a lot of carbon dioxide is released during a volcanic eruption. And usually it's not necessarily dangerous to human health unless it becomes cold enough that it becomes denser than the air, in which case it will sink. So cold CO2 sinks and will often lie in low-lying areas. So in a volcanic valley, in a lake, in a crater, you could have pockets of this sort of cold CO2. And this is undetectable by us. We cannot see or smell it. So this is why they tell you not to camp sort of in a volcanic valley, just in case there is a pocket of CO2 there, because you could go to sleep at night and possibly suffocate and not wake up. So that's just sort of an invisible danger to be aware of. Then we have sulfur dioxide, which is an irritant to the eyes, skin, and respiratory system. Sulfur dioxide is known for producing volcanic smog and acid rain. So along with your ash plume and ash fall, you can also have sort of a fog that sets in, and this is usually sulfur dioxide in the air. It looks like smog. Our next gas is hydrogen sulfide. This is really only very toxic in high concentrations, like upwards of 500 ppm. That will result in death for a person. But usually as humans, we can detect this in very, very small amounts. Because it is a sulfide, it smells sort of like rotten eggs. So if there is a strong rotten egg smell in an area, you sort of want to evacuate, because there could be hydrogen sulfide lingering there, which isn't good. And then lastly, we have our hydrogen halides. And our hydrogen halides are strong and very toxic acids. So they are very dangerous because they have a high solubility. So they can rapidly dissolve in water droplets, which can then cause toxic acid rain. The hydrogen halides also have the capability to coat ash. So as your ash rises up into the surface, it's carrying these toxic acids, and then your ash will fall somewhere. And this can then poison agriculture. It can poison drinking water. It's just not good for anybody. And then another hazard we have are pyroclastic flows. These are generally known as the sort of most dangerous part of a volcanic eruption. They're also known as pyroclastic density currents. But these flows contain a high density mix of hot lava blocks, pumice, ash, and volcanic gas. They move at a very high speed down volcanic slopes, and they typically flow into valleys. Most pyroclastic flows consist of two parts: a lower basal flow of coarse fragments that move along the ground, and then a turbulent cloud of ash that will rise above the basal flow. And these flows can be very hot. The extreme temperatures of rocks and gas inside of these flows are generally between 200 degrees Celsius and 700 degrees Celsius. So looking at this picture was taken during the day, so it sort of just looks like this gray cloud rushing down the side of a mountain. But if you look at a pyroclastic flow at night, it'll most likely be either red or orange, just due to sort of all the heat of the stuff flowing down the side of the mountain. But pyroclastic flows can also lead to secondary hazards, like many of our other hazards that we've talked about. They can mostly lead to flooding in lahars. Lahars we already talked about because they sort of clear everything out of the way. Rainfall happens, you get a mudslide. And then it can also lead to flooding because they do tend to roll down into valleys, which will contain a river. And so this is a lot of stuff entering into that river, and it can sort of block up or dam that stream and then cause later flooding. So in the last hazard, we're going to talk about our volcanic landslides. I think you've already heard a lot about these from Jessica already, but we're just going to sort of touch on them again. So volcanic landslide is different from a lahar because it's a landslide and not a mud flow. They're sort of like what you would think of as a regular landslide, except they can be very large and travel at very fast speeds. So if you know anything about the Mount St. Helens eruption in the United States back in the 1980s, that had a very characteristic volcanic landslide because Mount St. Helens sort of bubbled up, and then as it erupted, a side of it sort of blew off, and then you had this huge devastating landslide that sort of extended for many kilometers. But these can be common on tall, steep, and weak volcanic cones, and they're very characteristic. So looking at this picture here, you can see our volcano, and then one side is completely slumped down. So usually you'll see this slumped sort of texture on one side. And then as you get to the bottom flat portion, there is what's called hummocky texture. And that's just sort of all the bigger boulders and chunks that have sort of rolled off the edge of the mountain. But volcanic landslides can be especially dangerous if the volcano is close to water, because they have the potential to trigger a tsunami. So this volcano most likely did end up triggering a tsunami just because this material looks like it pretty much entered the water over here. You can see bits and pieces lying there. So that's what makes volcanic landslides particularly dangerous, the entering of sediment into a large body of water. So now we're going to move on to talking about specific volcanoes and the hazards that were associated with them. We're just going to talk about sort of their recent eruptions. So leading with Mount Agung. So this volcano is located on the island of Bali. It has an elevation of around 3,000 meters. Just to be more specific with that, so here is the island of Java. Bali's right next to it, and Mount Agung is sort of the easternmost volcano. There are multiple volcanoes on Bali, but Mount Agung is to the eastern side. And Mount Agung has had multiple cataclysmic or major eruptions, I should say. There was one in 1843, but there was a larger one in 1963 that we're going to talk about that had a VEI of 5. So what does VEI stand for? VEI stands for Volcanic Explosivity Index. So like I said at the beginning, there are non-explosive eruptions and there are explosive eruptions. So a non-explosive eruption is a category 0 on a VEI. The 1963 eruption of Mount Agung was a 5. So this is a paroxysmal eruption. That's what it's called. And these only happen every however many hundreds of years. So I already mentioned Mount St. Helens before with the volcanic landslide, but that one was in the same category. So obviously the higher the number, the bigger the explosion, usually the more cataclysmic. But on March 17th of 1963, the volcano erupted, sending debris 8 to 10 kilometers into the air and generated massive pyroclastic flows. And then these flows devastated numerous villages, which killed an estimated 1,100 to 1,500 people. Cold lahars followed these pyroclastic flows caused by heavy rainfall, and this killed an additional 200 people. So a lot of casualties. Here's sort of a hazard map, just so we can see sort of how far these hazards extended with a volcano that had an eruption with a VEI of 5. So sort of the warmer colors on this map are from the 1843 eruption, but we want to look at the cooler colors, so our blues and our greens. So first looking at this sort of medium blue color, this was our ashfall. So you can see that it pretty much extended almost the whole length of the island. A lot of ash impacted a lot of area. And then looking at this dark blue line, this was our lava flow. So again, not necessarily the most dangerous hazard involved in this eruption because it didn't extend very far, but everything in the path of that lava flow was probably buried or absolutely destroyed. And then our lighter blue line here is our pyroclastic flows that were so particularly devastating. And you'll see that our green line sort of follows that same pattern. And those were our lahars that followed those flows. So this eruption is a good example of sort of all the previous hazards that we talked about and the dangers they pose. This volcano also erupted in 2017. In September of 2017, this area experienced 844 volcanic earthquakes in just 1 month. So that's a lot of earthquakes for one volcano, even very much above average. So it had a lot of people scared that it was going to sort of blow up, but it's sort of been erupting on and off for the past couple of years. This eruption can be cataloged sometimes as the 2017 to 2019 eruption, just because it keeps starting and stopping so frequently. But this is sort of an example of how this many earthquakes is what sort of alerts people to an eruption may be about to happen and can sort of alert authorities to tell people to evacuate an area or just, warn people that there might be a sort of cataclysmic eruption that will happen. So this one is under very close monitoring because of all of this activity that is continuing. So our next volcano is Gelonggong, and I hope I said that right because it's a bit of a mouthful. It's located in West Java. It's an elevation of 2,100 meters. So to be more specific with that location, so it's this little red dot here. It's sort of located in a cluster of volcanoes on West Java. Java has a lot of volcanoes. In fact, a lot of the volcanoes we'll be talking about are located in Java. But Gelonggong is more towards the central side. There are other volcanoes of note on this map, like Papandayan. I think that one has had some recent eruptions. And then obviously Krakatoa is very famous over here in the Sunda Strait, but Gelonggong is over here. So this one had its last major eruption in 1982, which had a VEI of 4 and indirectly killed 18 people by traffic accidents and by starvation. But the reason I included this eruption was because it was relatively recent and also because it brought the dangers of volcanic ash to aviation to worldwide attention. So this volcano was erupting, there was a plume, an ash cloud, and 2 Boeing 747 passenger jets were flying downwind of this eruption, and then they suffered temporary engine failure and damage to their exterior surfaces. And so both planes were being forced to make an emergency landing at Jakarta Airport. So again, ashfall can be very dangerous to planes and human infrastructure, but this volcano is also a great example of looking at a volcanic landslide sort of texture that we see on the side of the volcano. So the landslide that happened here happened within the last 23,000 years, and we know that because of radiocarbon dating on the area. So here's sort of a topographic map of what that looks like. But here we're just looking sort of at the shape of the crater. And again, you can see this sort of slumped side. And down here we have our hummocky texture. Luckily, this volcano wasn't near a body of water, so it most likely didn't induce a tsunami, but we will be looking at volcanoes that unfortunately were near water and caused some problems. So our next volcano is Kelud. So this one is located in East Java. It has an elevation of 1,700 meters. So here again, located in East Java, in another sort of clump of volcanoes, but this one is more towards the central side of Java. This volcano erupts relatively frequently. It has a lot of major eruptions sort of over very short periods of time. I just put some of them down. There are a lot more more past eruptions that have happened that I didn't include. But these were particularly cataclysmic, I guess. So in 1919, there was an eruption that caused some lahars that were particularly deadly. There were around 5,000 people killed due to those lahars. In 1990, there were several large pyroclastic flows that were associated with that eruption. In 2007, there was no explosion. It was a non-explosive eruption, but it was categorized as a slow eruption. So there were volcanic tremors. People were sort of told to evacuate, but because there was no explosion, the volcanoes sort of looked asymptomatic, if you could say. There was no like symptoms of eruption. And so this caused evacuation issues, and evacuation issues are a common problem that can be associated with an upcoming volcanic eruption, just because, again, we can't predict them down to the minute. So sometimes warnings will come months in advance, and people don't necessarily want to leave their homes for months at a time or just have nowhere to go. And so this is just sort of a problem to keep in mind when thinking of mitigation techniques and keeping people safe during volcanic eruptions. But evacuation is sort of the best solution for a lot of those hazards, but also can be difficult to arrange because of the timing of an eruption. And then this volcano erupted in 2014 too. This one was explosive. It had a VEI of 4. And this eruption prompted 76,000 people to evacuate their homes. 2 people actually died after their houses collapsed from the weight of ash. And the amount of ash also caused the shutdown of 7 airports. So this caused issues with the distribution of goods. So ashfall was a huge issue with the 2014 eruption. And this picture was actually taken from there. So here you can see sort of the ash coating the houses and the vegetation, sort of like snowfall. And you can see it polluting the streams. And if we remember our hydrogen halides that possibly coated this ash, this could possibly be very toxic for this town. So then the next volcano we're going to talk about that you're probably tired of hearing about is Krakatoa. This is located in Sunda Strait, so south of Sumatra Island up here and north of Java down here. This one had a particularly large eruption in 1883. So this one had a VEI of 6. So this is classified as a colossal explosion. And this occurs every however many hundreds of years. So you don't see a VEI 6 very often. But just to sort of give you an idea of the size of an explosion that had a VEI of 6, this eruption was equivalent to 200 megatons of TNT going off. And that equates to about 13,000 times the nuclear yield of one of the nuclear bombs that devastated Hiroshima, Japan during World War II. So a explosion categorized as a 6 is the size of 13,000 nuclear bombs going off. So this was a huge volcanic explosion. And it had a serious consequence. At least 36,000 people died, mostly due to the tsunamis that followed this eruption. And the eruption destroyed 2/3 of the island of Krakatoa. And then following that, we have Anak Krakatoa, which is the child of Krakatoa, located in the same spot. So again, here was sort of the island of Krakatoa before the eruption. After it, 2/3 of it were blasted away after that huge eruption. And now we have Anak Krakatoa sort of growing in its place. And this volcano erupts very frequently, and so it's able to build itself up very fast. So here in this picture, you can sort of see it spurting a little bit of a lava fountain and continuing to grow. But this, its small size doesn't make it any less deadly because it erupted in 2018, which you've heard about in multiple presentations now, but this one had a VEI of 4. It erupted in December and then caused a deadly tsunami. The death toll was around 437. And so this makes this Anak Krakatoa's eruption the deadliest volcanic eruption of the 21st century so far, just because of the tsunamis that it generated. So you can see it has sort of all of the characteristics of our volcanic landslides that we were talking about. So we have our old summit up here, which is very tall and most likely very weak. And then it erupted, exploded, and part of it sort of slid into the water. You can even see the ring of sediment in this picture that caused an outgoing wave and a deadly tsunami, unfortunately. But this volcano also erupted in April of 2020, but there was no widespread damage, just a couple of lava fountains, which is very typical of this volcano. It's being monitored very heavily just because it does erupt so often, and it has the capability of building itself up sort of so quickly. The next volcano we're talking about is Merapi. So again, located in Java. It has an elevation of around 2,900 meters. More specifically, it's pretty much right in the center of Java. So it's the last volcano sort of on this trio of volcanoes that we see here in central Java. And Merapi, like Khulud, is another volcano that erupts relatively frequently. So there was an eruption in 2006. There were early tremors in April, and then lava flow began in May. So again, we have a bit of a delay between tremors and actual volcanic activity. So again, many people defied evacuation orders. But then on the 27th of May, there was a 6.3 magnitude earthquake that struck roughly 50 kilometers southwest of Merapi, which killed at least 5,000 people and left at least 200,000 people homeless. So again, sort of a link between earthquakes and volcanic eruptions. So we can experience earthquake due to an imminent volcanic eruption, or a large earthquake can actually trigger an eruption because there's a lot of shifting going around, and all of a sudden, if a large enough earthquake strikes, this can jostle something in a volcano and cause an eruption. But this was a very tragic earthquake that struck related to the volcanic activity of Merapi. So yeah. Then there was another eruption in 2010. This one had a VEI 4, so it was explosive. It erupted for about 2 months from October to December, and the death toll was about 350 by December. And then it erupted again in 2018, but this one was more of a phreatic eruption, and so it just caused sort of an immediate evacuation of the area. So then the last two volcanoes we're going to talk about haven't erupted relatively recently, but have been particularly cataclysmic. So I thought I'd include them just to, I don't know, for fun, I guess. So we have Mount Tambora. So Mount Tambora is located on the island of Sumbawa, so located south of Sulawesi here. So you can sort of see the size of this volcano in this picture. Here we're sort of looking down into the crater. And Mount Tambora last erupted in 1815 and had a VEI of 7. So this was a super colossal explosion. So you don't see these hardly ever, every however many thousands of years. But this explosion was so large that it was heard on Sumatra Island, more than 2,000 kilometers away. There were heavy volcanic ash rains that were observed as far away as Borneo. And the elevation of Tambora was reduced from about 4,300 meters to 2,800 meters. And then, although estimates vary, the death toll was at least 71,000 people. And this explosion was actually so large that it caused sort of a volcanic winter. So it caused a global climate anomaly. So 1816 became known as the year without a summer due to the impact on the North American and European weather. So in the Northern Hemisphere, there were crops that failed and livestock that died, which resulted in the worst famine of the century. So one volcanic eruption in Indonesia sort of caused a global effect and almost sort of an extreme tragedy just from one super colossal explosion. So then that leads us into the last volcano that we'll talk about, which is Mount Toba. So Toba is now known as Lake Toba. It's located sort of on the northern end of Sumatra here. So it's this sort of oblong lake that you see. And Toba is classified as a supervolcano. So people that know North America, we have Yellowstone, that's also a supervolcano. But the Toba explosion sort of dwarfs that in some aspects. So Toba last erupted 74,000 years ago, and this one had a VEI of 8. So this was a mega colossal explosion. And it had also been accepted that the eruption of this volcano led to a volcanic winter. So again, global effects, just like we saw with Tambora. And an explosion of this size is pretty much unimaginable. Just to give you an idea of it, we already talked about Krakatoa over here, which had a VEI of 6. So that's this sort of blue bubble. And if you remember, that explosion was equivalent to 13,000 nuclear bombs. So if you look at that circle compared to this huge sphere happening right here, it's pretty much impossible to imagine the size of the explosion that occurred with Toba. Even looking at Yellowstone over here, which also has a VEI of 8, is sort of dwarfed by this explosion happening at Toba. So then that sort of brings us to the end of this lecture. So in summary, we talked about important volcanic hazards like ashfall, lava flows, lahars, volcanic gases, pyroclastic flow, volcanic landslides, all very important to keep in mind, and also very important to sort of have a plan for each of these hazards. And then we looked at volcanoes that have had recent eruptions and the dangers they pose. But that's going to do it for this lecture, and I hope you enjoyed it. And I guess we can move to discussion and stuff now. Yeah.
Okay, thank you, Miss Hale Putra. So I think we still have quite a few minutes before the end of this session. So I will read some of the key points for the previous lecture. So the Indonesia lies in the Ring of Fire, which because it has so many active volcanoes. And these active volcanoes may lead to some of volcanic hazards, such as the first is tephra and ashfall that caused by explosive eruption and may endanger life, aviation, and infrastructure. And the second is lava flow that caused by explosive and effusive eruption, may travel to far distance from the source of eruption, and may lead to another hazard that causes by its extremely high temperature. The third one is lahar flow, which is lava flow that already mixed with water and surrounding, and may happen without volcanic eruption, and may cause serious damage to river valley and food pen, and also loss of lives. The fourth one is volcanic gas that released by volcanic eruption, such as carbon dioxide, sulfur dioxide, chloride acid, hydrofluoric acid, and etc. that may cause health problem and damage to vegetation and infrastructure. And the next is pyroclastic flow that caused by explosive eruption, can move fast and destroy everything on in it, cause secondary hazard like environmental damage, dam the river, and even cause of loss of lives. And the last is volcanic landslide, due to the acute steep of volcano that can cause similar damage like ordinary landslide, and it's especially dangerous if happen near the water because it may trigger a tsunami. So, okay, maybe we can start the discussion session. Anyone has any question? Please, anyone?
Hello, Harpan.
Okay, Mr. Juang, please.
I have 3 questions actually.
Okay. Please.
The first is, can we determine which signal was produced by seafloor volcano activity using SEISCOM-3? Because as you may know, here in North Sulawesi, we have a huge seafloor volcano. Yet all the earthquake information that we had disseminated from what I knew was produced by tectonic plate activities. That's the first question. The second question is, if the first question answer is yes, how can we predict whether there will be a tsunami after some, volcano activities? The third question is, does earthquake that caused by tectonic activities can actually influence seafloor volcano activities, etc.? I mean,
Okay.
and vice versa.
Okay, we'll see if I can remember those.
Yeah.
So the first one is there was an earthquake associated with tectonic activity, but you're wondering why it didn't trigger a volcanic eruption? is associated with one?
I think, Holly, I think he was asking whether their seismic system is called SEISCOM. It's just the
Yeah.
name of their system. Whether it's able to record volcanic activity. And since I'm a seismologist, I'll try to answer that question. So it may be that you have to look at the broadband data to see the evidence of the volcanic activity. But certainly seismology, yes, it's very sensitive to volcanic activity, and it shows up sometimes as long period tremor and sometimes as earthquake swarm. What was the second question?
But
oh, sorry.
But as you may know, sir, if there be some volcano activity, usually we just have one sensor that could catch signal like that. I mean, how can we actually tell?
Test the data, yeah.
Yeah.
Right. Okay. So this question of predicting the eruption based on seismic data, fortunately, the USGS has an entire group, a separate group of people that work only on this question. It's called the Volcano Disaster Assistance Team. So we have 5 or 6 people who work a lot in Indonesia with the agency which is responsible for volcano eruption. And their task is to give training on identifying the increase of seismic activity leading to an eruption. So I think I should say that we have an entire group working only on this question. And I think it's better if I contact you to this special group that works very closely on this big question. But it's based on the increase of seismic activity, yes. By the way, what's the name of the agency in Indonesia that's responsible for volcanic monitoring?
PVMBG.
PVMBG, yes.
Yeah. Okay, I wrote it down.
Okay, Mr. Juang, is that enough?
The second question, maybe?
That was asking if we could predict a tsunami around volcanic eruptions. So it's very hard to be able to predict that. It's sort of like trying to predict a volcanic eruption or an earthquake in the first place. I would imagine that people who work with tsunamis would sort of look at volcanoes that have particularly steep slopes, or at volcanoes like Anak Krakatau, which tend to build themselves up very rapidly, and so then tend to have weaker flanks. So then if it does erupt, it may trigger one. So a lot of volcanoes will be monitored if they are located near water like that, if they have particularly steep slopes, and if they erupt sort of on a frequent basis. So we can't exactly predict if a tsunami will happen, but we can look at the volcanoes where they might happen and then sort of plan from there. Look at like surrounding islands that might be impacted. If that answers that question.
Yeah.
Okay. Is that enough, Mr. Juang?
Yeah.
Okay, thank you. So is there any question regarding volcano hazard or volcanic activity in Indonesia? Anyone? Okay.
Maybe in the chat box. In the chat box, there is some question.
Okay. I see there is one question here in the chat box. Okay, I will read it for you. The first question came from Asher Octave from Gorontalo Geophysics Station. The question is, there are many types of volcanoes like Stromboli, Plinian, Hawaiian, which also have different types of eruption and the type of volcanic material released. How do tectonic process factors determine the formation of different types of the volcanoes, like its appearance, magma structure, and its eruption strength?
Okay, so this is a topic that I am particularly interested in,
Yes,
and
it's the very topic of volcanologists.
it's a very big area of research. I have mostly worked in the Cascades trying to sort of look at this question, but I guess I can start with saying that if you have sort of the more silicious the magma you have in a volcano, the more explosive it will become. So if you have a volcano that is more likely to produce magma that is andesitic or shosonitic or even lucidic, this will be very silicious and can produce very large explosions. And so looking at that in terms of a tectonic lens, usually in subduction zones, we will produce calc-alkaline basalt, which can sort of range towards the andesitic range to the basalt range. It all depends on the amount of sort of alkali material that you have in there, like your K2O and your sodium contents. So it very much does depend. I know that this is sort of a rambly answer, but it does depend. It's sort of hard to predict, but like a Hawaiian volcano will erupt mostly like tholeiitic type magma, so ocean island basalts. So that's why you get usually more non-explosive eruptions there. So those are your Hawaiian type, your VEIs of zeros. Whereas if you have a more subduction type one, you're producing most likely more silicious material, and you can get a more explosive eruption. Yes, that was a very rambling answer. I don't know if that exactly answered the question, but
Okay, but I think it's quite enough.
Okay.
So is there any? Oh yes.
One question.
Okay.
My name is Jimmy Nugraha from Research and Development Center. I want to ask a simple question about Sinabung eruption. You know, as we know, that's eruption from a few years ago until now. May you share your scientific opinion about the activities? Thank you. Sinabung
volcanic.
Yeah.
Sinabung volcanoes.
Volcanic. Yeah.
Wait,
Sinabung
sorry.
volcanoes. Sinabung volcanoes in North Sumatra.
Didn't you hear about Sinabung activities? Volcanic activities have eruption a few years ago until now.
Sorry, my audio keeps cutting out like a phone call, so I keep missing
Mr.
it.
Jimmy, can you please repeat your question?
Yeah, I want to know your maybe you're sharing about scientific opinion about Sinabung eruption. As you know, Sinabung have eruption a few years ago until now, right? In Sumatra Island, Sinabung volcano.
I don't know if I actually know that eruption. So
you haven't heard about the Sinabung volcano in North Sumatra?
I don't think so. I think that I think I may have heard of that, but in regards to a tectonic question, but I don't know the details of that eruption very well. So I can't technically answer that accurately. So I'm sorry.
Okay.
So
not major.
Is that all right, Mr. Jimmy?
Yeah, I think.
Do you have any other question, maybe?
No, thank you.
Okay. So I see that there is another question in the chat box from Miss Nurvita Fatmasari. The question is, what is your opinion about how to evacuate from pyroclastic flow when it's travel in the ground and some of it travel like a cloud to the direction of your place, which is only a few kilometers away?
Okay, so pyroclastic flow, at least in my experience, the only real way to sort of escape it, because there's no real way to stop it, is to have an evacuation before it can occur. So that's sort of one of the problems with people not wanting to evacuate when there are sort of seismic disturbances, and people recommend that you do evacuate just because there's really no other way to sort of avoid a pyroclastic flow because it will sort of destroy everything in its path. So it's not like you can put up a dam to block it. They will tend to flow into valleys and whatnot. So as long as you can get maybe to some sort of higher ground, that might protect you. But really the only way to sort of get out of the way and get out of the way in time is to sort of evacuate when there is a call to do that.
Okay. I see there is already plenty of questions in the chat box. The next question is from Mr. Edi Santoso. The question is it possible to use the seismic tomography method to image and estimate the movement of magma to estimate how big the eruption will be?
Maybe, I would refer that to more of a Walter question.
Okay.
He's more of the tomography.
Yeah, maybe it's kind of a geophysics question.
Geophysics question. Okay, so the question was whether you can use seismic tomography to estimate the volume of the volcanic eruption. So the answer is yes. A very good way to do this is with ambient noise seismic tomography. Ambient noise seismic tomography, because ambient noise tomography uses relatively high frequency surface waves. So when you have a high frequency, you have high resolution. However, it is also useful to include gravity data to look for the low density and magnetotelluric electrical data. Recently, some papers combine geophysical methods and are very successful. It's a very good question, and yes, we can see the magma, we can locate the magma chamber, and we can estimate the volume. Yes, with seismology and other geophysics.
Okay, but can you predict where will it erupt?
No, you predict an eruption with a different technique. You predict the eruption with the seismic activity. So they work together. The seismic activity tells you when will be the eruption. The seismic tomography tells you how big is the magma chamber.
Okay.
You have two pieces of information.
Okay.
Two useful pieces of information. One is the location and size of the magma chamber. The other one is predict the eruption.
Okay, thank you, Walter. I think it's quite enough to answer the question. Okay, for the next question, we have question from Mr. Yoga Mahardika from Earthquake Regional Center in Bali. He has two questions. The first question is, can tectonic earthquake activity, volcanic activity, can a tectonic earthquake activate volcanic activity in a volcano and why? And the second question is, if there are two volcanoes located nearby, like Mount Agung and Batur, or Mount Lokon and Mount Ampung, can it activate volcanic activity with each other? Can it influence each other?
Okay.
Okay, can I start the question of whether earthquake activity will trigger a volcano?
Okay, please, Walter. Okay, please.
Okay, you know what the very big earthquake was that occurred in Japan, Tohoku, magnitude 9.1. The only earthquake bigger was Sumatra. And in Japan, this huge earthquake occurred and almost no volcanic activity. Nothing was triggered. And as far as I know, from 2004 Sumatra, your famous Sumatra earthquake with terrible results, not much volcanic activity was triggered. So I don't think there is a strong connection, no strong or frequent connection between earthquake triggering the volcano. The volcano seems to be triggered more by the volcanic plumbing. By the volcano itself, by the interior of the volcano. Maybe that was question number one. What was question number two?
Okay, the question number two is, if there are two volcanoes located nearby, can the two volcanoes influence each other in
Go
terms
ahead.
of volcanic activity?
Go ahead, Holly. What do you think? two volcanoes near each other, do they interact?
I would say it definitely heavily depends on sort of the plumbing of the volcanoes. So, for instance, if their magma chambers are actually connected and they're sort of two separate vents to the same magma chamber, if you have like a basaltic dike or something that intrudes upon that andesitic chamber, this is then a hot material and maybe could trigger eruptions in one or both of those vents. But if their chambers are sort of separate, then it all depends on just how much pressure builds in that chamber. Yeah. So how much pressure would build in each individual chamber, sort of a thing.
Okay. I think that's quite clear to answer the question. Okay, I think we still have time to answer some question. The next question comes from Mr. Agung Saptaji. He has two questions. The first question is how to measure the VAI scale with instrumental or visual measurement. And the second question is there any possibility if any fluid magma activity at the inactive mountain, at the inactive volcano?
Okay, so measuring VEI, I think, I don't want to say that it ranges, but sometimes it can, like sometimes you'll see one volcano with a VEI of 4 and on a different list it's listed with a VEI of 5. So I think that there are some instrumental measurements with it, but a lot of it is like looking at plume height and the amount of ash that was produced, like in terms of square meters or kilometers. So just sort of the effects of the volcano. So basically how much of it blew up and measuring that. So you can look at that in a visual aspect, and you can also measure that by like seeing how thick the ash is, how widespread it is. But there are also other factors with that, like how much of it was blowing downwind, like how strong was the wind. So you have to look at the size of the crater it produced. There are many different factors that go into determining a VEI, and sometimes this can vary with opinion. So sometimes it's not exactly exact, but there are general charts that we have. Yeah.
Yeah, I would say that the VEI is a general description. It's not the same as like putting an instrument on the mountain and measuring an exact number. So it's a general description of the size. The second question was, is there any fluid, is it possible to record any fluid magma activity
in the inactive volcano?
Connected to an inactive volcano? Yes, of course. In fact, we make a joke. We make a joke that as soon as we put a seismometer on any volcano, we begin to measure earthquakes. So the joke we make is putting the seismometer causes earthquakes. In other words, once you have good measurement, you can see the activity. Maybe it will be low magnitude earthquakes, in many cases, not very strong. But yes, an inactive, by the way, Holly, what's the definition of an inactive volcano? How do you define inactive?
I guess just something that hasn't erupted within the past like 10,000 years or so.
Okay, so
hasn't had a lot of recent eruptions.
Hasn't had an eruption in about 10,000 years. That's what I thought. So of course it could still be potentially active. It could have a active magmatic plumbing, and it just hasn't erupted. So therefore we do expect to see sometimes correlated swarm earthquakes at inactive volcanoes.
Okay, thank you. I'm afraid our time for the current session is up. If there is still any question from the participant, you may post it in the chat box and I will collect it to send it to Ms. Saleputra so she can answer it later. Is that okay with you, Ms. Saleputra?
Yeah.
Okay, thank you. Okay, I think it's time to finish the lecture. Please give big applause to Ms. Saleputra. So this is the end of the first session for today's lecture. Then it's time to move to the break session. So I think it's time to give my place to Miss Madonna. Miss Madonna, please, the time is yours.
Yeah, thank you very much for Harman, and thank you very much for Howie and Astronaut. Maybe we take a break about 8 minutes. So we will come back at 10 o'clock, right?
Okay, thank
Okay.
you. Thank you, Madonna.
Yes,
Bye-bye.
thank
So short time.
Hello. Yeah, Miss Harfan, can you hear me? Harfan? Okay, thank you very much. Now, exactly 10 o'clock. Maybe time is yours, Arvan, to continue the next performance.
Oh, okay. We're going to directly go to the next lecture for today. The third lecture for today will be talk about tsunami-genic landslide that will be presented by Miss Jessica Reid. Okay, so Miss Jessica Reid, are you ready to present your presentation?
Yes, thank you.
Okay, okay. So please, Miss Jessica Reid, the time is yours.
Hello again, everyone. My name is Jessica Reid, and today I'm going to talk a little bit about tsunamigenic landslides. Actually, I'm going to talk about a couple of other things too. First, I'm going to talk about subaqueous landslides in general and where we see them, how they differ from landslides above water. And then I'll talk about the different causes of tsunamis that we see and how landslides fit into that picture. And finally, I'll do a quick summary of tsunami hazard mitigation, but in particular looking at where landslides fit into that role as well. The first question is the difference between subaerial and subaqueous landslides. Subaerial just means anything that initiates above water, whereas subaqueous is specifically when a landslide initiates below water. And these subaqueous landslides can have a couple of different characteristics. They have the potential to be bigger and faster and accelerate more quickly. Often we see debris flows and turbidity currents with much longer runouts and much greater volume involved. We also see some slumps and more recognizable landslides, especially where active tectonism is occurring. The image on the bottom of your slide shows kind of a cartoon of what a turbidity current looks like. And this is a really common part of continental margins. And I wanted to show on the upper figure is the famous Storega slide. It's kind of famous in the world of submarine landslides. And you can see it's absolutely enormous. It's about the size of Portugal. And it occurred a really long time ago, 8,000 years about. But it had some characteristics of submarine landslides, which is why I'm bringing it up. It featured very low angles and high mobility with a runout of about 800 kilometers. And it involved glacial deposits and silt, and also happened to cause a tsunami. So what causes these subaqueous landslides? It's pretty much the same story as landslides, subaerial landslides. It's a battle between resisting forces and gravitational forces, although the balance is sometimes changed a little bit. For example, sedimentation at continental margins is a little bit different. You have also wave loading and different kinds of erosion than you might have on land. And I wanted to give a little more about Storegga because I think it is kind of a cult classic in landslides. The name Storegga actually means big edge because it was a popular fishing place. It had this cold waters upwelling and bringing a lot of nutrients and fish into that area. So it was known for, and people didn't really understand why this was happening until more studies went into it. And another interesting feature of the Storegga slide was that it occurred retrogressively, meaning it started at a lower point in the slope and kind of crept upwards, kind of like in a sand dune, you might see this happen. And this is another common thing that we see in subaqueous landslides. Another place you can see evidence of subaqueous landslides is any continental margin. I chose this one because it's close to where I live, so I'm particular to it. You can see canyons and evidence of debris flows and all kinds of erosional features that really shape these continental margins. This is a sediment thickness map of the world, and you can see that passive margins like the east coast of the Americas, or also deltas like right next to India, you see high thickness. And passive continental margins have their own kinds of subaqueous landslides. They're often very big and shallow and feature debris flows and turbidity currents, long run out. And they're not very famous for producing tsunamis, but it's kind of a growing area of interest by some people in the field. Another, I think this is interesting, place that you see subaqueous landslides is in lakes. These are, this is Lake Lucerne in Sweden. And there's a history of a landslide event in 1601 in Lake Lucerne, which actually caused a tsunami that was 4 meters tall. And if you look at, there are some studies that have been done on what this lake looks like on the bottom, and you see the little blue dots represent debris flow deposits. You see head walls everywhere and exposed slip plains. It's clear that a lot of history has happened in these lakes. Here's another place you can find submarine landslides. This is the Hawaiian island chain. And you'll notice the kind of gray color corresponds to any slumps that may have occurred. Another thing that happens around here is debris avalanches. And these things, particularly slumps, can also cause devastating tsunamis. And this is just due to the active piling of material from the volcanoes and constant readjustments of the weight. So the study of subaqueous landslides has, I have to admit, been motivated by tsunami hazard assessment. Although it's kind of unbalanced because you can see from this pie chart that it's generally recognized that earthquakes make up the majority of tsunami causes. According to, this is 2013 data from the NOAA National Geophysical Data Center, and landslides alone only cause about 3% of tsunamis. And then in combination with volcanoes and earthquakes, you get a total of about 8% of tsunami events caused by some factor of landslides. But I want to point out that there is a large slice of this pie that is unknown in the dark blue. And I also want to point out that earthquakes are very easily measurable from far away. It's much easier to notice that an earthquake occurred than to notice that a submarine landslide occurred. So I want to put a little bit of grain of salt into this data. I also wanted to check out what is going on today. So on the left here, I pulled up information from 2020. So this is the most recent information from this database. And you can see pretty much it stayed the same. We have more uncertainty, and we've taken a little bit out of the earthquake section, but it's pretty much the same. And I also wanted to check out Indonesia in particular. And you can see that more tsunamis in Indonesia are caused by volcanoes than the global average, although landslides only make up less than 1%. So it's kind of interesting to look at how people are understanding in a holistic way what causes tsunamis. But another way to look at this is in the map. So I put information here about tsunamis that were caused in some way by volcanoes, sometimes a combination of earthquakes and volcanoes or landslides in volcanoes. And you might notice the Krakatau event is labeled as a volcano tsunami, although really we're not quite sure how to categorize if an event is purely volcano or if there was a landslide component. Another thing is the earthquake map. You can see that this map is dominated by blue dots, meaning most of these tsunamis are attributed solely to earthquakes, with only a few exceptions. And one of these blue dots you might recognize, the 2004 tsunami. We can also look at tsunamis involving landslides, and it's a pretty empty field. And you'll notice that there's only one yellow dot out there, only one event that was considered to be caused just by a landslide. And most of the dots show that earthquakes work in conjunction with landslides to create these tsunamis. The yellow dot is in 1979 a subaerial landslide, meaning it originated above water but then fell into the ocean. Actually, I checked some of these other accounts out, and a lot of them were subaerial landslides that fell into the water. And that made me wonder, well, those events are easier to notice. It's easier to notice if a cliff disappeared or if there's a huge landslide than something that might have happened under the water. So I'm just going back to how maybe this data is not fully robust in submarine landslides. Another interesting point is tsunamis with unknown causes. A lot of these incidents occurred in the 19th and early 20th century. The latest account I found in this map was in 1929, when a high wave capsized a boat and killed 6 people. And there were no seismograms that picked up this event. So maybe it's possible that this event was caused by a submarine landslide. Maybe it wasn't a tsunami at all. I think it's important to keep in mind that with tsunami data, we don't really have a history of accurate data collection. And it's really only in the past couple of years that we're able to rely on the information we're getting. I also wanted to look at some of the more well-studied events like Palu and Anak Krakatoa, which we've talked about so much, and mention that both of these events were initially caused by volcanic eruption or earthquake activity, and they both had a secondary hazard of landslide, which ultimately triggered tsunami. So it's a common pattern that happens there. Here's an interesting study that was done. You see the red circles, and they mark tsunamigenic landslides, known tsunamigenic landslides. Maybe you recognize number 6, a famous tsunamigenic landslide. Maybe not. I don't have much perspective anymore. And the white circles here represent evidence of submarine landslides. You can see a lot of white dots out there that we don't really have any links to tsunami events that they might have caused. They're just evidence that maybe we can reconstruct a connection between them and a tsunami, but it was hard enough to find the evidence in the first place. And this brings up a question that I have to ask, which is this 5% that we have here, maybe some of it was caused by submarine landslides, but we just couldn't find the money or the interest or the time to investigate that cause. So this is the event that I was alluding to. Yesterday we talked about liquefaction and how the Palu 2018 event really opened up liquefaction as a topic to be discussed and understood by the community and the world at large. And maybe a similar thing happened in 2004 with tsunamis in the Indian Ocean. And this was an equivalent for submarine landslides. In 1998, a moderate magnitude 7 earthquake occurred off the north coast of Papua New Guinea near Aitape, which is just about 130 kilometers from the border with Indonesia. And it generated a very large tsunami, which arrived at the nearest shore in about 20 minutes. You'll see that the concentration of run-up measurements is very narrow. And this event only affected those 25 kilometers of coastline for very strong run-up. And if we remember about past tsunamis that were caused by earthquakes, they usually affect maybe 100, maybe 250, maybe 300 kilometers of coastline. So it's a much longer range. You'll notice little blue run-up measurements in Japan, and those actually only measured 25 centimeters. So, but within these 25 kilometers of coastline, right next to the earthquake event, run-up was 10 to 15 meters high. So very high run-ups within a very narrow area. And it was a devastating event that killed more than 2,000 people. And it surprised everyone. According to the earthquake-based models, the tsunami was too large, and it also arrived too late to be caused.
Swakelola. Kalau dari kemarin sih.
Okay, maybe I'll continue. Yes, it arrived too late to work with the earthquake tsunami models that we knew. And this really motivated scientists to investigate whether maybe there was a secondary cause to these run-ups. Maybe there was a landslide. So a lot of interest was generated, and people started doing bathymetric surveys of the area. And they actually found that there was a slump. It's hard to see here, but this is one of the bathymetric surveys that they undertook. And they found a slump and did a model based on the landslide that occurred, and found that these run-ups, yes, they could have been generated by a landslide like the one that occurred off the coast. And this was really the moment in 1998 when landslide-generated tsunamis entered the mainstream of tsunami research, and people began to construct different models and look at past events that might have been influenced by a secondary contribution of a landslide. The study of submarine landslides, though, is expensive and time consuming. You need a bathymetric survey and you need a lot of information about the event. In Palu, we could see coastal retreat from satellite imagery. You can see these little boxes show all the instances where we could clearly see coastal retreat. And we could even estimate how much retreated and how much material was involved from the surface. The figure on the left is just one example of those little white boxes. And this is an interesting study that was done using both these known landslides that we could see plainly. Those are designated as S in this upper left-hand photo. And they also hypothesized some underwater landslides, some submarine landslides, shown as L here. And they made a model based on that and compared their results to observed run-up. And this is kind of as far as we know how to go so far without actually going out there and trying to find the landslides themselves, is kind of mixing the, letting it stay at a hypothesis instead of finding the evidence. So post-tsunami modeling would ideally help us to more accurately forecast the tsunamis. And tsunamigenic landslides have, in some cases, been identified as a contributor, but only after the fact. And really, the landslide tsunamis, for the most part, can't be forecast the same way that these earthquake tsunamis can. And so that's why most tsunami early warning systems are based off of earthquake evidence. And this involves accelerometers and broadband seismometers and many, many tsunami stations. It also involves sea level monitors. So on the left, you see an image from a satellite altimeter showing unusual sea level after the 2004 Sumatra event. This is really exciting and cool, but it doesn't really work as a tsunami detector because these satellites can't hang around all day, day after day, waiting for a tsunami to happen. So what really happens is tide gauges and deep ocean monitors. Coastal tide gauges were first designed to record low frequency events like lunar tides or seasonal changes. And that meant their sampling frequency was only about 6 or 20 minutes. And it works great for tides, but tsunamis are much higher frequency and were often could be missed. And actually the 2004 tsunami really changed the attitude on this, and a lot of tide gauges were updated and their frequency of sampling was increased to every 15 seconds to every minute, which is enough to detect a tsunami wave. But this is already at the shore.
Ms. Reid, you have 5 minutes left. You have 5 minutes left.
Okay, thank you. So this is what the lunar tide gauge looks like, and with the 2004 tsunami there. Another way you can measure the sea level is by looking at the deep water sea level. And this is a bottom pressure recorder. So you can use bottom pressure to calculate how high the water column is above you. I'm gonna hurry up now. This is what a tsunami event would look like with a DART station. Usually the sampling time is every 15 minutes, but it increases once it detects an event down to even 15 seconds. Another interesting area of improvement is creating or attaching these bottom pressure sensors with cables. This is an example that's happening in Japan. And one of the most exciting things is attaching all these instruments, seismometers and bottom pressure readers, to telecommunications cables. So it would have a smart cable that would be able to not only detect tsunamis, but it wouldn't need to be as maintained as the DART buoys. So I won't talk so much about this, but the idea is that with traditional tsunami early warning systems, it's really based on the earthquake. You detect the earthquake, you determine the hazard based on the earthquake, and you create your real-time model also based on information from the earthquake. Eventually, you'll actually detect the tsunami wave, and this is really the only part where you might gain information on a possible landslide contribution. But unfortunately, the way tsunami systems work now is they just feed that information on the sea level back into your real-time model, which actually changes our understanding of the focal mechanism of the earthquake and doesn't consider the possible contributions of a landslide to the run-ups we're looking at. Here's a close-up of what that might look like. And all of these are possible earthquake scenarios. I put this slide here just for reference. I'm not going to go into it because it's mostly earthquake models. But if you're interested, a lot of these are open source and you can go check out what they look like. So really the future of monitoring landslide induced tsunamis is, in my opinion, looking at the sea level is all we have right now. And there are different ways people are thinking of doing that. They're thinking of ship tracks or these smart cables, or even using high frequency radar to look at the sea surface. And I think that that has a lot of technological advances in the near future, which is very exciting. And that's all I have. Thank you.
Okay, thank you, Ms. Jessica. So we have saw the presentation about the tsunami-genic landslide or landslide that likely to trigger a tsunami. Before we go to discussion session, let me summarize a little bit about the previous lecture. So we've talked about tsunami-genic landslide, or we can call it subaqueous landslide that causes heavily affected by the resisting forces versus the gravitational forces that affected by some factors such as sedimentation, earthquake, erosion, wave loading, glaciation or deglaciation, and etc. that may lead to change to the land strength and stress. Some of the places where the subaqueous landslide most likely happen is in continental margin, lakes, and volcano near a water body. In Indonesia itself, there are some cases where the tsunami is caused by landslide, caused by a combination of volcano and landslide, and caused by combination of earthquake and landslide. And for today observation and studying a submarine landslide, the thing that we need especially is a bathymetry image where we can use it to estimate the volumetric change due to the landslide. And in terms for tsunami mitigation, one thing that we should do in order to mitigate the tsunami hazard is, the first is to establish monitoring station using seismograph to detect if is there any shaking that might causes landslide, and satellite image to detect if there is any change in land topography due to the landslide, and also establishing that gauge, buoy, and smart cable to detect the tsunami wave. Okay, maybe we can directly go to the discussion session. Is there any question regarding the presentation? Anyone?
Okay, if there isn't any question, then I will ask question to Miss Jessica. Right? Miss Jessica?
Yes, hello.
Okay. I want to ask about how can we link some tsunami event in the past that tsunami event in the past is caused by a landslide, not by an earthquake. How can we identify that?
Well, there are some landslide models that have been developed, and they mostly take into account the volume of the landslide and some kinematics, so the timing is important. But if there's a, I think if there's a, if you do a bathymetric survey and end up finding a landslide, a submarine landslide, then you have a tsunami in mind. You might have even timing data on that. And
well, I think another factor, Jessica, you mentioned it very clearly in Papua New Guinea, that it was only 25 kilometers of the coastline that experienced the high run-up. So the first indication that it could be landslide generated is the localization of the inundation. And we see this in many examples, that it's not spread out over a large area, it's more localized. And you emphasize that point when you discuss Papua New Guinea.
Yeah, thank you. And we've also seen this before in tsunamis that have been caused primarily by earthquakes, that there might be concentrations of higher run-up, and there's a hypothesis that they might be caused by a local tsunami, or sorry, local landslide.
Well, that, you just reminded me, another characteristic of a landslide-generated tsunami is that it doesn't fit the timing that you would expect for something coming from the trench to the shore. It can either be too early or too late. And I believe in Papua New Guinea, you emphasized that it was very late.
Yeah, the idea was that the landslide itself was a slump that was actually caused by an aftershock of the original earthquake. That the aftershock was the one that tipped it over the edge and caused that slump to trigger the landslide or the tsunami.
Okay, thank you, Ms. Jessica. So is there any question?
Now, Jessica, you said that it was the 1998 event in Papua New Guinea that made people think seriously about submarine landslide generated tsunamis. Is that right?
Yes, people had theorized before, but there was a lot of doubt. And in the case of 1998, they really went for it. I think there might have been 4 different surveys that were involved. A lot of people went out and took bathymetric surveys and really invested a lot in the possibility.
So the point that I would like to make for all the participants from BMKG is that if you really study any earthquake, you're going to find something about that earthquake which doesn't fit, which is not what you expect. A good example, of course, is the Palu earthquake, which had many characteristics we didn't expect. But in the United States, every time we have an earthquake, we find something unique and unexpected. So we learn from every event. Thank you.
Okay, thank you, Walter. Okay, there's already one question in the chat box from Miss Nurfita Fatmasari. The question is, I just want to clear understand. So, a tsunami event that could be caused by landslide, it's called tsunami-genic landslide. Even the main cause of the landslide happen is the earthquake or volcanic eruption, not the landslide itself. is everything that could be tsunami event that could be caused by landslide is called tsunami-genic landslide?
You know, I'm not sure, but I imagine that a landslide or a tsunami could be categorized as a tsunamigenic landslide or a tsunamigenic volcano if they're all involved in the same event.
Well, I think normally we would say earthquake triggered submarine landslide. So the earthquake triggered part is explained. Volcano triggered landslide. That would be the long way. Then very quickly it becomes tsunamigenic landslide because people don't want to repeat every time the whole long, everything, so such a long phrase. But we can add the part about earthquake triggered, volcano triggered.
Right. And it talks a little bit about the order of things too. You know, you might have something that triggers another thing that ends up actually generating the tsunami.
By the way, another characteristic of landslide, tsunamigenic landslides is that the run-ups are usually can be very, very high. They're local, they're very local, but they're very high, 10 meters, 12 meters, because it's almost like a splash. So I think we can use many factors to suspect the landslide origin.
Okay, I think the answer is quite clear. So I think we still have time maybe to answer one or two questions. Oh, okay, there is new question. The next question from Indah Kurniawati. The question is tsunami landslide can happen for all type lakes or just lake formed by fault activity?
Well, these subaqueous landslides can also be triggered by any kind of pore fluid movement. So if the pore fluid is redistributed, maybe due to sedimentation rates changing or some kind of erosion, then that can also generate a landslide. Sometimes these landslides are not as destructive as something triggered by an earthquake. Sometimes they can be.
Okay, thank you. Okay, maybe for the last question is for Mr. Aziz. Mr. Aziz, please state your question.
Okay, thank you. My name is Aziz. I'm from the National Earthquake Center. You clear my voice clearly? You hear my voice clearly? Okay.
Yes, we can hear you.
My question is, there are different, especially from the frequency content from the tsunami wave, from the tsunami-genic earthquake and the subaqueous landslide. Because correct me if I'm wrong, I think tsunami-genic earthquake is moved by one big force that slipped by the earthquake, so it's one big force. Then rather than subaqueous landslide, that one continuous force that slip for 1 point to 1 point. So I think it is maybe different. There are frequency different from the tsunami wave. Do you get my question?
So,
okay, Jessica, what he was saying is that with an earthquake generated tsunami, you have a sudden earthquake movement with a certain frequency content, maybe abrupt. Whereas a landslide could be, you know, a slow slump or something. It have a different frequency. So the tsunami wave may have a different shape, longer period, shorter period. The source, in other words, the source is a different frequency. I agree, it's a different source.
And we often see shorter wavelengths for these landslide tsunamis.
Okay, Aziz, is that enough?
So you mean that landslide maybe contain a more long period tsunami wave, etc. Or
Could be, but the you need to have tide gauge measurement for that. So I was working in Chile in 2010, and there was a big earthquake and tsunami. So I talked to people and I asked them, how many tsunami waves and what was the timing of the tsunami and how big were they? So people told me they gave me a lot of information from the eyewitness report, and I took a lot of note, but nothing seemed to agree very clearly. I feel very confused. So then I realized the tsunami came at 3:45 in the morning, nighttime, and there was no light, and nobody can see their watch. So I wonder, what about the information I'm getting? You know, nobody can see anything, yet they want to tell me everything. So what is my point? My point is sometime we really need the instrument recording. We need instrument recording to know really the period. You're asking about the period. We cannot rely only on eyewitness, because maybe the eyewitness, he wasn't even there. He just tells what his brother told him or his uncle. Anyway, Jessica, go ahead.
Okay, thank you.
Well, I was wondering about, with the 1998 event, there were tide gauges on the coast of Japan that recorded the event. And that's far away, so there might be differences in how that the landslide tsunami behaved far field, but it would be an interesting thing to look at those.
It's pretty far away. Yeah, the frequency would disperse, but yeah, you can try it.
Okay, I think we are already a few minutes late to the next session. I think it's time to finish this current lecture. Maybe if any of you still have a question for Ms. Red, you can post it in the chat room, and I will collect it and send it to the Ms. Red, and she will answer it later. Okay. Okay, I think it's time to finish this lecture. Thank you, Ms. Red, for the nice and informative lecture. Thank you very much.
Thank you.
Thank you, Jessica.
Okay, so for the next lecture, we'll learn about the tectonic evolution of Southeast Asia that will be delivered by Carson Tunnel. Mr. Carson Tunnel.
Yes, hi.
Mr. Carson Tunnel. So
that was good, yes.
your presentation?
No. I'm ready to start though. It's good to see everybody. I'll go ahead and share my screen. First of all, I'll just introduce myself since I haven't talked to anybody or with any one of you yet. I'm Carson Tunnel. I'm with the Earthquake Science Center in the U.S. Geological Survey out of Menlo Park, California. And today I will be talking about the tectonic evolution of Southeast Asia. Just a quick outline. I will give a general review of the geological features in the area. Then I will be discussing the major data that is used to create different tectonic plate reconstruction models. And then I will be actually showing you a tectonic plate reconstruction model of Southeast Asia. So first, the geological review. As Haley mentioned earlier, this photo has been shown many times over the course of this lecture series. But you can see here all the different subduction zones, transform boundaries, the volcanics, et cetera, et cetera. But the area is a triple junction, which means that there are three different plates that are colliding, major plates that are colliding to create all of the different geological features. So you have the Pacific plate coming in from the northeast. You have the Philippine Sea plate coming in from that direction as well. Then you have the Indo-Australian plate coming in from the south. And then you have the Eurasian plate, which is coming in from the northwest. As I said, this creates all the major subduction zones, transform boundaries, the mega thrust fault zones that we see. It also contributes to crust extension as well as rifting in the area as well. All these produce the earthquakes and tsunamis that we are all too familiar with, and also the volcanics as well that previous colleagues have talked about. So for the major data that is used for the reconstruction models, probably the most important is going to be the paleomagnetism aspect of it. You can see here in this figure down here, this is just a basic explanation of that paleomagnetism. In the colored areas, you have the normal magnetic polarity, and in the white, you have the reversed magnetic polarity you see here. This is an example from seafloor spreading. But paleomagnetism is the study of the Earth's magnetic field. Shows us the orientation of the magnetic field at the time that the rock was formed. And this is done by testing the orientation of the magnetic, properties of magnetite in the rocks that are being sampled. And this actually gives us a better clue as to when the rock was formed as well. Because of this, it shows us the past position that any rock formation may have been in the past, and it can also reveal any kind of rotation or movements that the plate or rock has gone through. So next we have isotopic dating. Typically argon, potassium, argon dating is used. Potassium argon dating is used more for igneous rocks, just due to the higher content of potassium in them. But argon dating is a lot more accurate. So again, as I mentioned, it is mostly used on igneous rocks, and especially in this area, there's a ton of igneous activity and rocks in the area. And it also helps us construct a story about when any kind of volcanic event may have happened, or any major subduction occurred as well. Another very important tool to use or create these tectonic models is seismic surveys. It reveals different structures under the crust, including, and probably most importantly, is any kind of faulting or trenches, and especially any kind of subduction zones as well. And this is important for subduction zones, especially because it will give us the dip angle of the subducting plates, which then will also reveal the rough age of the subduction zone as well. Just as an example, you can see here a just rough seismic survey. And then here you can see the interpretation of that survey. So you have the continental crust on this side, and then the oceanic crust on this side. And then you can see the actual subduction of that oceanic crust under the continental crust, which is highlighted by that black line. And again, that gives us the angle, which tells us the age. Next is seismic tomography. This is based off of P-wave velocity measurements. We can see exactly how the plates are interacting with each other. And again, this gives us another way to look at the dip angles of the subducting plates. And it also shows us that, oh, excuse me, I meant to explain the difference in the P-wave velocity. So oceanic plates will have a higher P-wave velocity. You can see that in the blue here, and here as well. And then the continental plates will have the high or lower P-wave velocity, as you can see here. And this figure is just showing several different survey locations that you can see here. A to A prime corresponds A to A prime. And these all cross the Molucca Sea plate. So the next tool that we use for tectonic plate reconstruction modeling is GPS coordinate movements. These highlight the margins and the plate boundaries by showing us the direction of movements by the plates themselves. And it gives us an average of the velocity of movement of these plates as well. Because of this, it further shows us or gives us an idea of the tectonic complexity of the region. And it also allows us to extrapolate the past plate movements and positions based on any kind of recent GPS readings we may have on hand. And so I will get into the tectonic plate reconstruction. So again, they are used to show the history of plate movements and also the formation of regions and any kind of tectonic activity that may be happening at the present moment. This one in particular that I will be showing is presented in increments of 5 million years and begins at 160 million years ago and is provided courtesy of Robert Hall in 2012. So first is a GIF just of the entire model, just give you an idea of what you're going to be seeing. And then I will be explaining different slices of that tectonic model as we go along. So first at 160 million years, we start to see down at the bottom of this figure, you see India and Australia. And then you have the Argo and Banda blocks right here. These begin to rift from Australia at this time. And subducting begins beneath Eurasia on the southern edge and also between, the eastern edge of Eurasia as well. At 155 million years, the Woyla arc begins to form as subduction begins north of India. And there's some northward movement of India at this time. And then, of course, the Mesotethys Sea begins to reduce in size as well. And then from here on out, any ophiolites are going to be highlighted in green, as you see here. At 150 million years, the Banda and Argo fragments separate from the Sula Spur and further separate from Australia, as you can see with the red line representing a spreading center between them and Australia. At 145 million years, the Woyla arc also separates, as far as naming convention in this model, into the Incertus arc. And this actually, this arc formation actually begins to move northward as well, because there's the extended rifting between those arcs and India. At 140 million years, more subduction occurs north of the Banda block as it and the Argo blocks move northward. And then you can see a sort of extension of that subduction extending out into the Pacific Ocean. And then this line right here is a transform boundary, which the Banda arc and Argo arcs will start to move along, which will eventually get them into the place that we see them now in Southeast Asia. At 135 years, triple junction was formed, as I explained, with that transform boundary, but it's more evidenced at this point in time just based off of rock records. And the Banda and Argo arcs are renamed to Southwest Borneo, which used to be Banda, and then East Java, West Sulawesi, which used to be the Argo block. At 130 million years ago, India and Australia began to rift, as you can see by that red line between the two. And again, just to highlight, there's the renaming of the blocks there. There's some subduction south of East Java, West Sulawesi, but that's not very important at this time. At 125 million years, there's again further rifting between India and Australia. The Synotethys begins to widen because of this. At 120 million years, Southwest Borneo and the East Java, West Sulawesi blocks begin to move closer to their final position. As you can see, they're nearly there. At 115 million years, subduction between Southwest Borneo and East Java, West Sulawesi begins, and certain anomalies in the Synotethys are labeled with their age as we move forward, just to highlight that along the spreading centers, I meant to say. At 110 million years, Southwest Borneo is in its final position. Spreading ends in the Synotethys between, I lost that part. Oops, sorry about that. Anyway, 105 million years, East Java, West Sulawesi, and Southwest Borneo converge. The Woyla and Syrtis arc are approaching Sumatra at this point, and Java as well. And then you can see off the east coast of China, the Leuconia dangerous grounds converge with Eurasia as well. At 100 million years, spreading continues between India and Australia, and India begins to move northward as well. At 95 million years, widening of the Synotethys occurs. This is due to India and Australia spreading and India's continued movement northward. At 90 million, spreading between India and Australia ends for a short period of time. India continues its movement northward at an even faster rate, and this is shown as the IA transform boundary in the dotted white line. East Java, West Sulawesi begins to dock at Sunderland, and the Leuconia dangerous grounds finishes its docking with Asia at this moment. At 85 million years, subduction ceases around Sunderland for the moment, and spreading between India and Australia begins again to the southeast of India. At 80 million years, India moves northward at an even faster pace. Magmatic activity is recorded in Bird's Head, which is the northwestern part of New Guinea. And for now, I show a slice of the model just to give you a recap and let you see that movement up until this point. And then at 75 million years, India continues to move north as expected, while we see no real movement from Australia at this point in time. The India-Australian transform boundary begins to subduct beneath Sumatra at 70 million years. As a result, magmatism begins in Sumatra, and at this about at this moment is when the eruption at Toba occurred, as mentioned by Haley earlier. At 65 million years, subduction beneath West Sulawesi begins, and this is also marked by volcanics. And several intraoceanic arcs form in the Pacific at this time. At 60 million years, a strike slip margin south of Java and Sumatra begins to form as Australia moves its northward movement and pushes plates and rotates them. At 55 million years, India begins its collision with the Enceladus arc, which then becomes accreted to northern India. At 50 million years, the Philippine Sea Plate begins to form due to spreading within and around intraoceanic arcs in the Pacific. And then the sepic terrains arrive at New Guinea as well. At 45 million years, Australia moves north and new subduction zones form south of Sumatra, Java, and the Philippines. The Proto-South China Sea begins to subduct north of Borneo and the Philippines as well. And spreading actually begins in the Celebes Sea and the Philippine Sea as well. At 40 million years, India's movement starts to slow as it is nearly in contact with the Eurasian plate. And the India-Australia transform boundary continues to subduct under Sumatra. At 35 million years, the Proto-South China Sea continues to narrow due to its subduction. At 30 million years, spreading begins in the Proto-South China Sea, and new crust is forming, which then becomes the current South China Sea crust that we know it as today. At 25 million years, the Sula Spur begins to make contact with the North Sulawesi volcanic arc, as you can see there. And the Philippine Sea Plate rotates clockwise due to movement along strike slip boundaries in that region as well. At 20 million years, spreading ends within the South China Sea, and as a result, its subduction ends as well. The Molucca Sea begins to subduct beneath the Celebes Sea at this point as well. At 15 million years, subduction rollback of the Celebes Sea causes spreading in the Sulu Sea. The Java Trench begins to roll back into the Banda embayment at this time as well. And northwest of Australia, this causes extension of the Sunderland margin. At 10 million years, continued rollback into the Banda embayment causes even further extension of the Sula Spur. This causes the North Banda Sea to form, and Andaman Sea spreading begins as well. And then finally, at 5 million years, there's even more rollback into the Banda embayment, which causes the South Banda Sea to form at this time. And the Halmahera and Sangahe arcs were about to collide at this point in time as well. And again, just another short GIF of just to recap the last little bit. And that's it. The main thing that I have to say, in order to get more accurate reconstructions, we do need to gather more data. Like I mentioned, more paleomagnetic data and seismic surveys, as well as isotopic data gathering would be needed. There really isn't a whole lot of that data gathered in this region. Really, most of the data gathering was done during the 80s, and then there was like a slump of that data gathering, and then it slowly started to pick up again. But that is what is most needed at this point in time to create more accurate construction model, and that would give us further information as to what's going on tectonically in this region, and possibly even help us understand why earthquakes occur where they do. But I thank you for listening to my lecture. I really appreciate it.
Okay. Thank you, Ms. Carson, for your interesting presentation. So before we go to the discussion session, let me summarize a little bit about the presentation. So we just learned about the tectonic evolution of Southeast Asia, and tectonic plate reconstruction used to show the history of plate movement. And the tectonic reconstruction study was using a method like paleomagnetism, which identified the orientation of magnetic field in rock that was assumed to represent a tectonic plate, and that may be used to reconstruct of the orientation of the plate movement. And some other methods is isotropic dating that was used to identify the absolute age of a rock so that we may know the time when the plate move or interact to each other. The other methods to do plate reconstruction study is a seismic survey to reveal the fault structure and show the deep angle of subducting plate so that we may interpret the dynamics of tectonic plate. And the other method is seismic tomography that can be used to interpret the plate interaction and reveal the edge of subducting plate. And the tools for plate reconstruction study for the most important is using GPS coordinate movement so that we can reveal the margin and plate boundaries, plate movement, velocities, and the past plate movement. And some interesting fact of the result from the Southeast Asia reconstructing study is that it is revealed that Banda and some part of Eastern Indonesia is used to become part of Australia continent. So that's why some geologic feature like rocks or biological feature like endemic animal in eastern part of Indonesia is very similar with the one that existed in Australia. Okay, so I think it's time to start the discussion session. Anyone want to ask question?
Yeah, I have a question.
Okay, Mr. Jimmy, please.
Yeah. Thank you for your excellent presentation, Mr. Channel. I'm Jimmy Nugraha from Research and Development Center. I have a little question about, I'm focused in Makassar Strait to see a tectonic develop there. There's so much debate among geologists about whether the area is spreading or rifting. What is your opinion about it? And then the second question, I want to know if you have experience in file survey to take a sampling technique to take a sample, make a measuring isotope measuring. Thank you.
Okay, so as far as the Makassar Strait, I saw that there in this particular model from Robert Hall, and he talked about it only briefly. He believes that there was some spreading in that area. He didn't really touch on it as far as this model is concerned, unfortunately. I mean, I honestly can't give an expert opinion on that. Unfortunately, I would have to do more research.
Okay. Because I think there's so many geologists debate about the tectonic process in Makassar. And then, do you have any experience to take a sampling for isotope?
I unfortunately don't have any experience with that. I do have classes that are available for me to take at university, which I intend on taking, but I'm still working on my degree, so I should have that done soon. or be able to experience that.
So I have a question, if I may ask. So Carson, according to Robert Hall's reconstruction, every piece of Indonesia seems to be a separate small microcontinent. You know what I mean? Borneo
Yes.
has many pieces. Sulawesi has the Sulu Spur, then it has northern. So what is your opinion of how reliable is this reconstruction? Will it change a lot with time, or is it stable?
I think for right now, it's the most stable that we have. I have seen some of the past reconstructions that even Hall has done, and he has placed those certain blocks just already in Indonesia as well. But that didn't seem to line up with any kind of data that has come out since his past reconstructions or others' reconstructions that will place those certain blocks in various areas at different times. For example, the paleomagnetic data and the isotopic dating is some of the most important, which lends to the fact, or I guess explains why those blocks are more likely to originate in certain areas and then move to their final locations at the times that they do.
Okay, so the short answer is you feel that it's quite well constrained and,
Yes.
and reliable.
Yes.
Okay, thank you.
Okay, Mr. Jimmy, is that enough?
Yeah, I think it's now. Okay, thank
Let's
you.
move to the next question. There is already one question in the chat box. It's from Mr. Iputu Dedi Pratama of the Denpasar. So the question is, when Australia land reach the megatrust zone in South Indonesia, will it be a collision like India or a subduction?
I believe it's going to be more of a subduction just because you have more actual continental crust coming from the Australian plate. It might be a little bit difficult to explain, but I think it's like the Molucca Sea plate that's being subducted between the Halmahera and Sangahe plates. You see those are acting somewhat similarly, I think. I mean, there is the question of the trench there, but I don't think that it'll be a collision like how India collided with Eurasia.
So I think it's quite clear. So we'll move to another question from Mr. Reza Ida. The question is, what make isotopic dating is more accurate in creating tectonic plate reconstruction model?
So isotopic dating just gives us the year that it's formed, and I think it's more used in conjunction with the paleomagnetic data. So they feed off of each other. So if you have both, that gives us a more accurate dating system. And that way we can tell when the rock was formed, or sorry, the landmass was formed, and like in the situations where you have subduction and forearc and back arc creation, you can tell when exactly that happened, and then you can more accurately create the model based off of that.
Okay. Is there anyone want to ask question? Maybe regarding the methods of plate reconstruction of the findings after the result of plate reconstruction in Southeast Asia.
Nathan, maybe there are questions on YouTube. Yeah.
Oh, okay.
I have posted on chat box.
Oh, okay. I see that the question is about how to calculate the landslide material volume to mapping the future landslide tsunami. I think it's a question from for Miss Freud, Miss Jessica.
Yeah.
All right.
How to calculate the landslide material volume to map to model the future landslide tsunami.
Okay, maybe she is not here at the moment. So I think this is difficult because you cannot be sure what the landslide material volume will be. So the result is you have to take different estimates, a very high estimate, a medium estimate, and low, and make three calculations. Because to be honest, we don't know in advance how big the landslide material will be. It's the same with an earthquake. Sometimes an earthquake begins and stops, and just the earthquake magnitude 3 or magnitude 4. But other earthquakes continue and grow to be much bigger. So we don't have that understanding yet. We don't yet have a good understanding what's the maximum. So you have to try different value, not just one.
Okay. Okay, thank you, Mr. Muni, for the answer. Okay, I think I see a question for Mr. Channel from Mr. Bayu Pranata. The question is, from paleomagnetic methods, can we predict when there is a magnetic field reversal?
I'm not entirely sure, but my gut feeling would say no. I think there have been stretches where the magnetic field has stayed stable for a few 100,000 years to a million years, and then it just suddenly swaps to the reversal or the reverse direction, and then within a short period of time it switches back. I don't believe that there's any way to any real accurate predictions.
Yeah, so I agree with you. The Earth's magnetic field is due to convection currents in the outer core, the movement of the liquid outer core. It is not regular. It is irregular, and it's a very difficult problem even to calculate the changes that occurred in the past using computer. So computer calculations try to show the model for the past magnetic reversals, and these are very difficult. So I think we cannot predict the next magnetic reversal.
Okay, I think that's a very clear answer. So is there any question for Mr. Channel? Anyone?
Maybe you have to check out a participant. There are two participants raise hand.
Okay, please.
Aziz or Jimmy?
Okay, Mr. Aziz, please state your question.
It's actually my raise hand. I forget to lower my hand.
Okay. Mr. Jimmy, you want to ask question?
No.
Okay.
Cannot.
Okay. Maybe. Okay. There's a new question in the chat box from Mr. Zireza. The question is it possible when the Indo-Australian plate that plunge into the Eurasian plate break in the middle that it can produce a new subduction zone?
What do you mean by break in the middle exactly? Do you mean after it's already been subducting, the plate that's subducting breaks off, or do you mean the plate itself will split?
I think the question is about yeah, I think he asked if there any possibility that the plate that's subducting may break into some part that it can produce a new subducting zone.
Well, I'll try to answer that question, and then Carson can add more if he likes. What we have seen in this very nice lecture is that over the last 160 million years, there have been many changes in the tectonic situation and many new subduction zones. Things have rotated, subduction zones have been created in the middle of the ocean, and so on. So yes, it is possible. It's always possible for the Indo-Australian plate to break somewhere and for it to make a new subduction zone. We do not predict that. It's not what we are predicting, but it's possible to happen.
Okay, thank you, Mr. Muni. Maybe Mr. Tunnel, you have any additional answer to this question?
No, I mean, the only other thing that would have to change is, I mean, honestly, I don't have anything to add. I think he explained it perfectly. We don't have any predictions for it to change. I mean, we have what we have now, and that's just the model that we're going based off of. So.
Okay, thank you. It's all right. Okay, I think we still have plenty of times for this discussion session with the topic of the tectonic plate of Southeast Asia. Maybe anyone want to ask another question? Please raise your hand or just post the question in the chat box. Anyone?
Sorry, Harman.
Yes.
Maybe I have the basic question for Kazan and Walter. Maybe.
Miss Madonna.
Could be. Maybe I think this topic about paleomagnetic is the new for me, right? So according to you, yeah, right? There are a relation between paleomagnetic and paleoseismic. So they are, I think, influence each other, maybe.
Okay, maybe I can try to answer that. So the question was whether there is some relationship between paleomagnetic and paleoseismic. And paleomagnetic usually is talking about very long time periods, because the Earth's magnetic field only changes after several 5 or 10 or 20 million years. Whereas paleoseismic, we're very interested in earthquakes that happened 100 years ago and 200 years ago and like that. So they are different time, geologic time. However, one exception is from a volcano. If a volcano has a magmatic flow every 10,000 years, so you have flow, the paleomagnetic will have a rotation, a small change of direction, not a reversal, just a change of direction. But I think these are completely different time scale, paleoseismic, paleomagnetic. Thank you for your question.
Is that enough, Miss Madonna?
Yes. Okay.
Okay, thank you. So is there anyone want to ask question? Okay, if there is anyone want to ask question, I want to ask to Mr. Tonal. Mr. Tonal, here in BMKG, we have a proton magnetometer that we can use to record magnetic field. Is that tools can be used to record the paleomagnetic in rocks?
No, this is a different kind of technique. The paleomagnetic requires a slightly different kind of machine. We can sense the reference for you for what kind of machine is used. We have some experts in Menlo Park who study volcanic rocks just like in Indonesia, and we have a big center here for paleomagnetic. So I can help any question on paleomagnetic. I can call upon the expert to give you the information for that.
I think that's great. So we still have 5 minutes left for this discussion session before we move to the next agenda.
I think there's a question on chat room number 23.
Oh, okay. Okay, another question from Firzi Reza. The question is, as you said, that it will possible. We use tomography method to detect the breaking to confirm the new subduction. I think it's related to the previous question about the possibility of the breaking of subduction zone.
Well, I think the answer is yes. The answer is that the seismic tomography is very useful to identify breaking slab and new subduction. And Carson, you showed some example that Zhang et al. Paper that you showed the cartoon, the color cartoon.
Right.
Go ahead.
Yeah, it's very possible. I mean, I believe it was Haley that was talking about it earlier, that tomography is used to show when there's any kind of, or I guess it was maybe Jessica, any kind of magmatic swelling up from the earth under volcanoes. It could be used in the same way, say for like rifting zones or anything like that.
Okay, thank you. I think it's quite clear. Okay, Ms. Madonna, is there any other question from the YouTube channel?
Not yet.
Okay.
Maybe you can open a question for the previous material.
Okay. So if there isn't any question for Mr. Tano presentation, maybe we can start the discussion session to answer the unanswered question from previous lecture. So I have been collecting 3 questions, and 3 of them all for Miss Red, Miss Jessica. Miss Jessica, are you there? Miss Jessica?
Hello. Yes, I'm here.
There's already 3 questions that still unanswered for you from your last presentation. So I will read it so you can maybe answer it. Okay, the first question is, if it compared with the 1988 Lituya Bay tsunami, how are the similarities and difference with the 2018 Palu tsunami event? As I know, the 1958 Lituya Bay tsunami was a landslide tsunami triggered by the earthquake.
I'm sorry, I don't know very much about that earthquake tsunami, so I can't give information on that. I apologize.
Right. Okay. So the next question is for Miss Reid. I think it's the same question. Sorry. Okay. Okay, so if any participant want to ask any question that we've been discussed so far for today's lecture.
Jessica, can you tell me again the question that you didn't answer? I had stood up just for a minute and I missed it. Can you repeat it, Jessica?
A comparison between the 2018 Palu tsunami event and the 1958 Lituya Bay tsunami.
Oh, well, these are very different. Okay, the Lituya Bay tsunami was one very large landslide in a very contained region. Well, I guess in that sense they are similar. This was a very well studied landslide event. It had a huge run up. I mean, it was tremendous, the tremendous wave height, tens of meters, very, very localized and in a very contained, very restricted area. So in the general way, you can say that they are similar. At the same time, the Palu Bay is much longer. It's about 60 kilometers long, and there are some differences in detail, but they are worth comparing. So it's an interesting comparison, and both are well studied and documented. So they're interesting. The Lituya Bay is Alaska, and it was, there's a long report about it.
Right. Yeah.
It's a very good question and fascinating comparison.
Okay, thank you, Mr. Muni, for the answer. Okay, so I have another question from Mr. Agung, and I think it's question for Miss Hale. Miss Hale, are you there?
Yeah, I'm here.
Okay, so the question is, can Toba supervolcano erupt again or reactivate again?
Yeah, it most definitely can. So just like with Yellowstone, it's classified as a supervolcano, and these things only ever really erupt every however many thousands of years. So it may not erupt immediately, but maybe eventually it has the possibility of erupting again. So usually we monitor supervolcanoes, like Yellowstone is pretty heavily monitored to see if there's any dangerous activity surrounding it. But yeah.
Okay. So the answer is yes.
Oh yeah, sorry. The short answer, yes.
So there might be chance that the Toba supervolcano might erupt as big as that it was erupted before with the, okay. So maybe that might have a very, very destructive effect. Okay, there is another question from YouTube. YouTube for Miss Hale. The question is, what do you think it is possible that VAI scale volcano eruption can exit the previous one? I mean, it's maybe there was an explosion that on a scale of 9 VAI.
Yes. So I would say that the VEI of a volcano is very much dependent on the type of magma erupting. So like I said before, if you have a more silicious magma, you will have a more explosive eruption, so probably higher up on the VEI scale. And it's also dependent on how much pressure has built up in the magma chamber over time. So a volcano could have multiple eruptions with a VEI of like 2, so not very explosive. But if a lot of magma suddenly fills up the chamber, or there is maybe like a hot intrusion that will cause hydrous minerals to dehydrate, this can then up the pressure in a chamber and cause a more explosive eruption. So the amount of silica can also change in magma over however many thousands of years. So a volcano may become more explosive the more silicious it becomes. So yeah, VEI can change.
Okay, thank you. I think there is still a question from the same person. The question is there any relation between the earthquake activity to the volcano activity, volcano eruption?
Sorry, my Zoom froze. I missed like all of that.
The question is there any relation between the volcanic eruption with the earthquake activity?
I think that Walter sort of answered that when he answered a different question about earthquakes that trigger volcanic eruptions. And so he said that he thinks that there are very little influence from earthquakes on volcanic activity. Tremors can result from a volcano that's about to explode. But I'm not sure if larger seismic events that are linked to like tectonic activity can influence volcanic activity that much.
Okay, thank you.
What we sometimes see is when you have a big earthquake, volcanoes both nearby and far away can exhibit some unrest, moderate or minor unrest, but not an eruption. It doesn't cause an eruption. They are shaken a little bit, and you see an increase in gas emission and micro earthquakes, but not, it doesn't trigger the eruption. Thank you.
Okay, thank you, Walter, and thank you for Ms. Saleh for your answer. So, is there any question? Any question for the previous lecture? Maybe for Miss Esther or anyone? So let's see.
We can end early today because you have to take the exam again.
Oh, okay. Miss Madonna, what about if we end the discussion early? Or we still have to wait for another question?
Up to you. Maybe
we can end
maybe
right now, so we will move to the post exam.
Oh, okay. So we can, if there isn't any question, so we could end it right now, and the participants should done their examination.
Do the post exam, yeah.
Is that all right, Ms. Madonna?
Okay. It's okay.
So,
It's okay.
Okay. I think we can finish this lecture for today. Thank you for Mr. Tono, Mrs. Woods, Ms. Putra, and Ms. Reid, and also Mr. Uni for the lecture and for the discussion. There was very interesting discussion. Maybe I will let Ms. Madonna to take over my place. Thank you very much for today.
Yeah, thank you very much, Harvan. Yeah, thank you very much, Walter, and thank you very much for Jessica Ray, Aswan Wood, Hale Putra, and Carson. Thank you for your performance and the great presentation. Gitu ya. Oh yeah, maybe today we will conducting a post test for all of participants. So maybe we haven't finished earlier. So I think the remind of the time remind of this session. I think I give opportunity to participants to prepare to face a post test. So I have oh yeah, Walter, maybe I wonder we can start tomorrow at 7:30 a.m. Jakarta time.
Okay.
13 minutes earlier because we must finish before 12 and to give time for Muslim to take a Friday prayer. So
okay.
Don't worry about that. Yeah.
So we start at 7:30 tomorrow, so we can be finished for the Muslim prayer. That's fine.
Yeah.
Okay.
Yeah. After the final the last session, the last lecture, we have actually to conduct the closing ceremonial. Yeah.
Okay.
Maybe yeah, I think that's information for me. So yeah, thank you very much for your attention and your appreciation for this lecture. Maybe as usual, Walter, do you have the closing statement for today?
Yeah, so thank you for all the questions that people asked and the great interest everyone showed. Today we had a very diverse set of lectures ranging from Ashton Woods on climate change all the way to tectonic evolution, and everyone had very good questions. So USGS will say goodbye because we will go to sleep now.
Oh yeah, right.
Thank you, Walter.
Thank you, Walter. Yeah, thank you. Yeah, because
okay.
Yeah, thank you, Walter.
Bye.
Bye. See you next tomorrow.
See you.
See you.
Have a wonderful afternoon, and we look forward to seeing everybody. Thank you.
Jangan lupa ya nanti hari ini teman-teman untuk post test pukul 3 sampai 3 sore sampai saya buka pukul 3 sore sampai pukul 7 malam. Jadi waktunya sangat leluasa. Namun waktu untuk pengerjaan soalnya ada 45 menit. Seperti biasa ya, seperti yang sebelumnya. Jadi istilahnya saya kenapa durasinya cukup panjang karena memberikan kesempatan teman-teman untuk mempersiapkan diri lah gitu. Ada pertanyaan terkait dengan masalah proses?
Bu Madonna? Bu, ini ada pertanyaan dari Mas Bayu. Mas Bayu minta referensi paper, Bu.
Tadi kayaknya udah dijawab.
Apa yang sulit didapatkan, bisa didapatkan di mana ya, Bu, selain di LMS?
Tadi kayaknya udah dijawab ya sama Walter ya. Coba bisa menghubungi beliau. Cuman kira-kira Bu Nelly, saya terus terang mungkin saya ingin Bu Nelly gimana Bu Nelly terkait dengan masalah referensi?